Does it work? No. Okay. Okay. Can you hear me in the room too? It works? Yeah, okay. Excellent. Okay, thank you, and very welcome everyone to Stockholm and the AGI-23 conference. So a lot of things have happened in AI since last conference, and I thought I would try to zoom out a little bit and look at the big picture. So here is a graph of the human population development over the past 10,000 years or so. And as you can see, it's going straight up, and it's following quite closely to technical innovations. Here, for example, is the Watt engine and railroads, the Industrial Revolution. And if we look at the human impact in terms of biomass, it's quite amazing. So 4% of the global mammal biomass consists of wild mammals like elephants, whales, and so on. 34% consists of humans. And the rest consists of things that we eat. So that's, we are dominating the planet. And if we look at the development of other species, then it's, as we all know, going down when it comes to biodiversity quite rapidly too. And this goes for all kinds of species. And if we look at the biggest causes of biodiversity loss, then it's things like habitat loss, overexploitation, pollution, and climate change. So all of those are human activities. So of course we are causing this development. So we are doing something like this right now, it seems. So we are facing a serious sustainability problem where we must learn to combine economy with ecology. And we need to become better at using technology, it seems, not least AI. And as we all know, there are lots of different unethical uses of AI already today, depending on how you define it. But things like fake news and mass surveillance are two examples. But there are also a lot of positive uses, such as diagnostics, drug development, and traffic safety. And in those cases, it could arguably be unethical not to use AI. So we have to try to understand the consequences of AI as good as we can. And it's clear that there is a huge upside. We can tackle a lot of sustainability goals by using AI. But also a huge downside. For example, as Hinton said, it is hard to see how you can prevent the bad actors from using it for bad things. And I think that's something that most people would agree to. So we might ask, do we understand the consequences of AI? Well, we've had a very fast development lately, so I think the honest answer is no for most people. But I also think that this is the common situation when it comes to technological development. I suppose it was the same thing when they invented the wheel, the printing press, and the computer. It was very hard to survey the consequences and look into the future. And if we look at the AI research community, it's pretty divided too on these issues. So clearly we need more research on the economic, political, and social consequences of AI. And just an observation, these are social science questions, so they are most fitting for social scientists and not so much for AI researchers, mathematicians, cognitive scientists, and so on. And we also need more speculation, I think, because we are trying to look into the future at these very important questions. But looking into the future, that makes it part of future studies. And that is sometimes counted as a part of social sciences. And sometimes people say that this is not science, this is only speculation. But even if it is only speculation, it is very important that we keep on speculating and thinking about these consequences. And finally, we need more regulations. We have a lot of regulations in sectors like food, healthcare, automotive, aviation. But for AI, we don't have it yet. But now one of the first AI laws is underway here in Europe. They just took a big step this week. Yes. And if we look at the state of the art, the current situation in AI, and compare what AI can do to what humans can do at different tasks, then, as we all know, AI is at the human level or beyond at many tasks. But let's not forget that there are still a lot of tasks that human can do better, just like climbing any mountain. We don't have rescue robots that can do that. Work in any home. We don't have service robots that can do it. Or drive on any road. We don't yet have autonomous cars that can do it. So we're still not all the way there, that's for sure. And if we think about what kind of tasks we are trying to solve with AI, then most of all, it is about man-made tasks. Like here are just two examples, like solving IQ tests and designed by psychologists, and playing games designed by people. But animals were not developed primarily to solve IQ tests or play Go. They were developed to survive and reproduce. So they are facing other kinds of tasks, like find food, find mate, avoid predators, avoid obstacles. So one might ask, how good is AI at solving those kind of questions, at surviving in challenging environments, like animals can do? Well, that can bring us to the survival games, where the goal is to survive. But sometimes it is not only to survive, but also to collect points or do some achievements. So here we have 4 different survival games: Breakout, Pac-Man, Crafter, and Minecraft. And AI is much better currently at those games because they are being played on fixed boards. It's always they always operate in the same worlds. So that's pretty easy for reinforcement learning algorithms, for example, to learn. But here it's much harder, where we have open worlds and worlds that the player has never seen before, such as in Minecraft. And then in those cases, humans are much better. But in those games, these games are not only about survival, so they are also about those achievements. And we were interested in looking at pure survival games, where the only challenge is to collect food and avoid obstacles. So we developed an AI algorithm that tries to survive, and it operates always in new worlds that it has never seen before, randomly generated. And then we compare human to machine performance. And in this case, humans are better. We also made another basic survival game of this kind, which is set in the game engine Unity, and we have generated a lot of different worlds, forest environments in this case, and trained reinforcement learning agents to survive there, in this case some kind of rabbits. So they run around in the forest where they have never been before, and they need to collect 2 kinds of food to survive. And here that's an overview seen from above, and this is the retina, and this is the gaze of the hare. So it's running around in this environment trying to survive, and competing with other hares. And it has to take obstacles into account in the form of trees and think about the slopes of the terrain where it will lose more energy if it tries to go uphill. So in this case, we got the opposite result. So the machine was better than humans. Well, it's not perfect, as you can see. The reason for that is probably that it's fairly hard to steer this rabbit with the keys, simply. But on the whole, we got a result which says that machines and humans are roughly equal at these basic survival games. So this was an example of a strategy for AGI to create AGI via cognitive modeling. And the main idea there is that if we can model animal cognition, and in particular human cognition, well enough, we will get AGI. So that's one of the avenues towards AGI. Another one which we have seen a lot of in the past year is generative models. So they learn patterns in human artifacts like text, pictures, music, videos, and they all predict what's going to happen next. And humans are really good like prediction machines, and so are the generative models nowadays. And one striking feature of generative models is that it's possible to use the transformer architecture in a lot of different for a lot of different purposes, like for computer vision, natural language processing, reinforcement learning, speech translation, and all of those can actually be tackled with one and the same architecture, which is pretty fascinating. So one architecture works for many different purposes. And the same thing seems to be true of the human brain, which has a neocortex divided into 6 layers. So it looks essentially the same in many different places, like in the visual cortex and motor cortex and so on. So the same architecture is able to process many different sensory modalities. But again, we are not there yet. So here is an interesting example from Stuart Russell, who reported an experiment where a pretty average human player challenged the best computer Go playing program, which is far better than AlphaZero. It's called GBX Kata 005. The computer got a big handicap too. And they started to play, and Go is about surrounding, basically. So black is the computer, and it has started to surround the white pieces. So it's going well. But in the meantime, white, the human player, started to surround the group that is surrounding. And eventually that went well, so that the human player actually outperformed the program in this case. And this suggests that neural networks can't really represent the key notion of Go, which is that of surrounding groups. Even though it's excellent, it can't really conceptualize it like humans can do. And here is an example from ChatGPT. And I wrote there, suppose it takes 5 hours to dry 5 shirts in the sun. How long does it take to dry 10 shirts? Okay. And then it answers, yeah, okay. Then we can assume that each shirt takes 1 hour to dry. This implies that the rate is 1 shirt per hour. And then if we have 10 shirts, it should take 10 hours. But we have common sense, so we know that, well, it will be enough with 5 hours for those two, right? So I'd like to thank our keynote speakers so much for accepting to give keynotes here. Irina, Anoop, Noah, and Martin and Tom. And our sponsors, especially Digital Futures and SingularityNET and AGI Society, of course. And to our committees who have done a great job here with Marian, Patrick, Robert, Matthew, Haley, Vlad, Birger, and Pei. Thanks so much. Yeah. Exactly. And finally, I hope you will enjoy the conference, and don't forget to look at Stockholm too. Thank you very much. You can take mine.
Oh, we're being streamed. Right. Good morning, everyone here in Sweden for AGI-23, for our technical keynotes day and our keynote speakers. Welcome all to our AGI-23 conference. Welcome to everybody online, people who are watching us all around the world. Hi to all of those of you who recognize that we're at a pivotal moment in humanity as we now approach the final breakthrough in the final countdown to artificial general intelligence. Now that AI has come into our daily use, for people who don't use AI, people who aren't technologists can now start expanding their productivity, expanding their impact on the world with generative AI models and with other tools. So it's never been a more exciting time to be in the field. It's wonderful to be here. My name is Janet Adams. I'm the COO of SingularityNET, and I'm here supporting the conference to introduce our speakers today. First off, I'd like to say a big thanks to Claes Stranegard, Claes, who has just given us such a brilliant opening keynote. Thank you very much indeed. It's lovely to zoom out and get the big picture of where we are in time and exactly where we are to frame the abilities of humans versus AI for the day. Claes is the Gothenburg University Professor of Data Science and AI. He's the chair of the conference for today. He works in teaching cognitive sciences and AI and has research interests in human reasoning, agent-based ecosystem models, neural networks, and pattern finding in cancer registry data. So big thanks to Claes, A, for chairing the whole day, but B, for such an excellent and inspiring opening keynote. Thank you. And now I'm delighted to move us on. We're currently running 9 minutes late for those of you tracking us online. We've got a really thought-provoking keynote coming up from Tom Zimke. I hope am I pronouncing that right? How should it be? Zimke, from Tom Zimke. Welcome, Tom. Thank you so much. Tom is going to talk about time to move on. AI and cognitive science need a divorce. And this is a hotly anticipated and debated topic. Tom is a professor of cognitive systems at Linköping University in Sweden, where he leads the Cognition and Interaction Lab, which is part of the Human-Centered Systems Division at the Department of Computer and Information Science. He's a prominent voice in the areas of embodied cognition, social interaction, and in particular, people's interaction with different types of autonomous technologies, ranging from social robots to automated vehicles. We look forward to hearing his expertise on how people interpret AI and interact with him. Big thanks, big welcome, Tom.
Okay, this seems to be working. Am I heard all right? Okay. Okay, well, thanks for the invitation. It's a little unusual time to talk on a Saturday morning, but guess there's a first time for everything. Okay, yeah, as the presenter just said, the title here is Time to Move On. AI and Cognitive Science Need a Divorce. Yeah, title is of course supposed to be a little funny or provocative here, but I'll explain what I mean about that in the end. And of course, I'm not saying AI and cognitive science have nothing to do with each other or they shouldn't talk to each other. It's just that, well, yeah, we'll get to that point. Okay, so let's see. Just a little bit about my background. My training, my original training is in computer science, but then I've drifted into cognitive science like 25, almost 30 years ago. And so I went very much from neural networks research to neural networks in robots to human-robot interaction. And this is just an illustration of some of the types of AI that I'm looking at right now. And what I'm most interested in is not the AI as such, but people's interaction and interpretation of AI. So here are just some examples of standard robots, and sometimes they look human-like, sometimes they look not human-like at all, and sometimes they're automated vehicles or something like that. And the thing that I'm most interested in is maybe the picture here in the middle. What goes on? How can that person interpret the behavior of the automated car there? How does that person know what the car knows, and how can it predict its behavior? And that's of course not a trivial question, but that's how the AI and cognitive science combine here, because it's about what goes on in the person's head, but it's of course what goes on in the person's head is about what goes on in the car's head, apart from the fact that the car doesn't really have a head. Okay, so let's move on. These were just some examples. Okay, I'll give you a rough overview of what I'm talking about, which is 5 points. And this is basically the argument in a nutshell. So I'll give you the argument here in a minute, and then I'll give you the argument again in about half an hour. Okay, the first point will simply be that people, or many people, are confused about the relation between AI and human cognition. I think I see some people nodding, and Klaas already brought that up in his introduction to some degree. There's so much talk about AI, and so many people are not at all understanding what's going on, and many people are confused, but we get into that a little bit more later. And part of the problem is, of course, I would claim, is the close relationship that AI and cognitive science have had for a very long time, for, I don't know, 60, 70 years now. And in particular, this idea that cognition is computation, which has been absolutely central in both AI and cognitive science, or large parts thereof, for a long time. Then in the middle, this will be the biggest part. I'll talk about what's usually known as the symbol grounding problem, and then my variation of that, which I call the observer's grounding problem. And I'll talk about attribution of intentionality, which relates to what I was talking about earlier, how people interpret AI systems and robots in particular in terms of intentional agency. Okay, fourth step will be to say that another part of the problem up there, number one, another part of the problem is people's tendency towards what we call anthropocentric anchoring and adjustment. That means when they judge or explain or interpret what artificial systems do, they often start from human-like expectations, which is of course is correct in some cases, but it's wrong in many cases. Okay, and the fifth step, I'll get to that at the end, is that I'm claiming a healthier view of the relationship between AI and cognitive science, is that computational cognition and human cognition are completely different things. If you want to formulate in terms of the slogan here, I'm not at all against any claims about human level intelligence and beyond, but I'm saying it's not going to be human-like intelligence. But we'll get to that in the end. Okay, so then let's go through these 5 points. First one was people are confused. And yeah, Klaas already talked a bit about that. Talked about the stochastic parrot and then ChatGPT. Here's just a heading. And I'm sure you've all seen 100 headings like that. where AI simply is this, or chatbots are simply referred to as human-like. And what people don't understand about it is the parrot nature of the stochastic parrot. So people don't understand how something that produces a human-like output can do it in completely human-unlike ways. And just some other examples here. Another example, another completely different example of real-world AI. By the way, you might have noticed already, I use the term AI in a very broad sense. So I'm not talking about specific AI techniques, but rather computation AI in a very broad sense. Okay, so here's just an example. When this accident happened, you probably remember 2018 in Tempe, Arizona. Somebody got killed by an Uber. And one thing that when newspapers picked up on how did this happen and what exactly happened, one thing that many people picked up on was this thing that the car didn't know that that pedestrians could jaywalk. And that's, of course, again, this is an example of where something performs much of the time in human-like ways. So the car is driven for millions of miles in a human-like way and nothing happens. But then suddenly something happens and people get confused by that because they, of course, assume that, well, it's driven millions of miles with human-like performance. So how come it makes this mistake that everybody else, that humans would have avoided, because humans know that pedestrians can jaywalk. And this is, of course, again, this confusion about the performance and the competence. So what people misunderstand here is that human-like behavior, the perfect driving performance, was not achieved in any human-like way. Okay, so this is what I mean about people are confused, but what AI can and can't do. Since we're in Sweden, I just threw in here an example from Swedish media for an interview like a year or two ago with Daniel Kahneman, Nobel Prize winner, about 20 years ago. And so this is another instantiation of confusion. So when the reporter here asks him, is there anything unique about human intelligence? He explicitly says, I don't see what is unique about human intelligence. You know, we have a computer, and it, from the context it's clear, he refers to a computer in the head. And the idea that it's completely different kind of computer, it doesn't make sense to me. So this is just an example. We don't need to go into Kahneman's work or any of the details, but this is just an example of a leading psychologist referring to this idea that, well, what people have in their heads, of course, is a computer, he seems to be saying. And that's, of course, part of this general attitude in the AI and cognitive science that, that people make that assumption that cognition is computation, our brain is some kind of computer, and he explicitly says, I don't see any reason to question that. But the question is, it should be asked the other way around. I mean, what reasons are there to believe that the brain is a computer, not the other way around? Okay, so that was just to illustrate that point of people being confused. Okay, then point two was part of the problem is, of course, yeah, I already mentioned this, the close relationship between AI and cognitive science for such a long time. And again, I don't need to talk about this much detail. Everybody has seen quotes like this 100 times. Herbert Simon, for example, in 1960 said, yeah, machines will be capable within 20 years of doing any work that a man can do. And there's another example here from the New York Times back in '58. And they're predicting all sorts of things based on the very earliest instances of neural network research. Okay, so there have always been these grandiose predictions about AI becoming human-like at some point. And you can, of course, say, okay, but that was 65 years ago. Certainly today we know better. But we, of course, know that we don't really know better. I mean, there's still many textbooks like this one, Computation and Cognition, that argue for this computational view. Also, if you look up cognitive science on Wikipedia, just did that this morning, says one of the fundamental concepts of cognitive science is that thinking can be best understood in terms of representational structures in the mind and computational procedures that operate on those structures. So still today, people hang on to this view of cognition as computation. Then, of course, we should of course also say that many people have questioned this. That's just from a paper by Selma Bringsjord from 97. Many people have, of course, questioned this, and what about John Searle and so on. So people have also been questioning this view for 40 or 50 years. But really, yeah, it's still on Wikipedia, and still many people hold on to this. So this, the general idea has certainly survived, although many people have questioned it. Okay, that then leads me to part 3 here, where I'll talk a bit about the symbol grounding problem and different aspects of it. And the point that I'm doing here, doing this, is that I'm trying to illustrate with this particular example that, yeah, although many of these problems have been discussed for 40, 50 years, they maybe have been misinterpreted anyway. And that's why we still have this confusion, or still this widely disagreeing viewpoints on whether it is or isn't computation. Okay, the symbol grounding problem, again, I don't have to go into this. The symbol grounding problem was based on the Chinese room argument. And the whole point was, of course, that at that point, AI, yeah, by Searle, it was described as happening inside a room, isolated from the world. In the 1990 Scientific American paper, this was illustrated like this. The person looks at the symbol and knows what it refers to. The computer only sees the symbol. Okay, and that, you could say, that was AI back then. Since then, many people have, of course, worked on solving that problem, and they've taken these types of illustrations quite literally. They've said, well, okay, it's true, the guy is stuck in the room, he only sees the symbols and he doesn't know what the symbols refer to, so we have to make the symbols refer to something. And that's how people have approached it. And then people, yeah, there are different approaches to symbol grounding. This is just from a paper by Luke Steels, who wrote a paper explicitly claiming the symbol grounding problem has been solved, but there are many variations of it. Many people let the robots learn symbols or sub-symbolic representations in interaction with the environment. And some people now would also argue that the learning that's behind, the machine learning that's behind systems like ChatGPT is also some kind of symbol grounding. Okay, so there are, many people would argue that problem was a problem of old AI, of purely computational AI, but today we've solved that problem. And that, yeah, kind of seems to be true. I guess because, again, as I said, I'm talking about AI or computational systems in a broad sense. So I don't know if that particular lawnmower really is using any AI, probably nothing that's particularly interesting. But this is just an illustration of a robotic system or computationally driven system that works in the real world. And of course, it's not at all in that situation anymore. It is now in the world, people would say. It's in the world and interacts with the world. And it certainly seems to have representations of that world that help it to interact with that world, because this is, yeah, I think it's obvious. It's a lawnmower that has a charging station and that goes to that charging station when the battery needs recharging. So it's certainly, you would say, it has that kind of intentionality that Searle argued AI was lacking. This robot certainly has it, because it's intentional, firstly in the sense that it has a map of the environment, it approaches object in the environment. It's also intentional in the sense that, yeah, when it approaches the charging station, it does so for a reason. It does not just do that randomly. Okay, and that generally, of course, this was just the simplest example, but that generally, of course, also refers to, for example, automated vehicles, which have all sorts of internal representations of the world and reason about the world and act in the world and do it correct 99% of the time, but unfortunately not 100% of the time. So you could say, many people would claim that this clearly illustrates that, well, Searle was wrong, or Searle was maybe right about that time of that type of AI at that time in AI's history. But at this point, that problem simply isn't a problem anymore. Yeah, we can skip that. Okay, so that leads us to okay, so it's clearly the case that we can interpret robots as agents that have that intentionality that Searle was talking about, that AI systems traditionally were lacking. So let's have a look then at how people do that, because that's of course not just not something that I just made up for that particular case of the lawnmower and so on. But there's actually quite much research on this in recent years, how people interpret robots as intentional agents, which I just tried to illustrate with those simple examples. That means agents that have some kind of internal mental states that refer to the world, and that have beliefs about the world, that have desires, things they want to achieve in the world, and that have intentions, such as whatever, approaching your charging station when the battery is running low. So, as I said, there's lots of research about that in the last 10 years. We recently published a systematic review of 155 empirical studies of this. And okay, that's a very long and detailed paper, but just to summarize, we know roughly the determinants of how people interpret systems as intentional systems. That has to do with what the robot looks like. It also has to do with whatever the age and the motivation of the person. We also know a lot about the consequences of that type of interpretation. There are psychological consequences. For example, people trust systems more if they can explain them in intentional folk psychological terms. But it's cognitively draining to some degree. And there are, of course, also behavioral consequences. So interpreting systems in folk psychological intentional terms also make those systems more predictable and explainable. Okay, but there's still a rather big black hole here in the middle, because we still don't know very little about what are actually the mechanisms, the cognitive mechanisms that are underlying this. And that's exactly what we're working on. And this is just a quick illustration of a new project that we just started, where we're looking at how people interpret the behavior of different types of robots. And we're starting from some old cognitive psychology model from Nickerson from the late 90s, which exactly looks at how do people interpret. So his model was not about AI at all. It was about how people interpret other people, and how they go from how they start from their own knowledge and starting from their own knowledge, they derive some model of what other people know. So, for example, let's say if I was talking to some random person here, I could start from my own knowledge. I know I speak whatever German, English, and Swedish, but I know that not everybody at this conference is Swedish, and people outside Sweden rarely speak Swedish. So if I spoke to a random person here, I would not make the assumption that they speak Swedish, but I would make the assumption that they speak English, because otherwise what would they be doing at this conference? And so on. And there's of course also, you factor in long-term knowledge of specific others. Whatever, I see Christian Balkenius in the audience. I know he is Swedish, he speaks Swedish. We have many times spoken Swedish. So starting from my own knowledge and taking into account unusual aspects of my own knowledge. Only I know what I had for breakfast. And taking into account what different categories of people know, and long-term knowledge. People they start from their own knowledge, they come to some model of what others know. And we start using this as a starting point to look at how people interpret the behavior of different robots. And we're of course trying to get at, do they use do they use similar mechanisms? And is it in that case, are they, for example, more likely to ascribe human-like qualities to this robot than to that robot or that robot? Or what exactly are the relevant factors here? Okay, don't need to say much more about that. The fourth point I wanted to make was exactly what I just talked about. I'm trying to indicate here or argue that another part of the problem, again, the problem being people being confused. Another part of the problem is people's tendency towards anthropocentric anchoring and adjustment. That refers to exactly the picture that I just showed. And if you remember, I just said that's a model from cognitive psychology, late 90s. So this wasn't about AI at all. So question then is, of course, well, is there any evidence or are there any indications that people do use what we call anthropocentric anchoring, that they use themselves as an anchor or as a starting point? And of course there is, otherwise I wouldn't be talking about this. I just have here a couple of quick illustrations of how we've been studying this. This is a paper from 5-6 years ago where we asked people to look at pictures of behavior, both human behavior and humanoid robot behavior. And we asked them to explain what's happening, and we had a detailed look at how they explained that behavior. And one thing that we found was that they explained human behavior and robot behavior in very similar terms. They described just as much whatever desires, intentionality, and so on in the human case as in the robot case. I mean, there were some small variations. So, for example, this statement, "Alice makes a fantastic cake," was people were less likely to think that the robot had the goal to do that, and that might, of course, have to do with people eating cake and robots not eating cake and so on. Anyway, but the general result was people explain the behavior of people surprisingly similar to the behavior of robots. Okay, and you could say, well, all of this uses language. So we made people choose between certain categories and so on. And that, of course, since we use that type of language to describe human behavior, it's easy to fall into that trap and to describe robot behavior in exactly the same way, like like I did 5 minutes ago when I talked about the lawnmower. The lawnmower approaches its charging station in order to recharge its battery, or because it wants to recharge the battery. It's easy for us to fall into that trap, to simply use that kind of language. Therefore, we did another experiment where we assessed this implicitly. So we didn't make people talk about behavior, but instead we made them observe and predict behavior. So in this case, we're not asking what kind of mental states the robots might be having, but we're simply asking people to predict the behavior. This is a false belief task. We don't need to go into the details, but the important thing is the text there on the left, because the result in a nutshell was, as it says there, a majority of the participants in these experiments predicted the robot's actions based on anthropocentric assumptions about their visual and auditory capabilities. That means they were assuming that robots could roughly see, could perceive and hear exactly what people could hear. I mean, the setup, you maybe see it here, there are different visual conditions, a transparent shower curtain and intransparent curtain, and then there are certain conditions where the sound plays a role and so on. And the point was that people simply assumed that the robot could see and hear what people could see and hear. Okay, we've been studying this more in other setups with automated vehicles. This here illustrates a study where we asked people what they thought automated vehicle could perceive. And yeah, I think you can predict the result. Result in a nutshell in all of these studies is that people tend to assume human-like perceptual and cognitive capacities. So in this case, they assumed that the car could see what a human driver would have seen in the same situation. In this kind of setup where we made people predict behavior, they were assuming that the vehicle had capacities like object permanence, so that it wouldn't forget about objects when they disappeared from sight and so on. So the general result is exactly what it says there. People seem to assume human-like perception and cognitive capacities. Okay, and that brings us to what I call the observer's grounding problem, which is, yeah, you probably get it from the introduction, is a variation or reinterpretation of the symbol grounding problem, but now for different type of AI. Because if we look at this kind of scenario in this type of interactions, we of course, based on what I just said, just to explain the term here a little bit, we have a problem in the sense that this person is likely to interpret the behavior and predict the behavior of that car in folk psychological terms. I mean, how else is he supposed to do it? He's probably encountering that car for the first time. So of course he interprets the car as if it was driven by a human driver. And he's likely to make assumptions like that the car can perceive pedestrians, that the car knows there's a crosswalk, and so on. Those are of course reasonable assumptions. And of course he uses his own grounding for that. But it's of course also another passing of just the term observer's grounding problem is that it's the observer's problem. We're no longer talking about the grounding of the AI system being the problem. It's the observer's problem, and it's his grounding that is the problem. I have a quick comparison here. So in the original symbol grounding problem, the AI system was considered to be the problem, and people thought that the whole point was that the symbols in the AI systems lack grounding or aboutness or intentionality, whatever you want to call that. And in embodied or robotic AI, people think the problem can be solved or has been solved in some technical sense, you could say. Whereas in the problem I'm trying to point out here, it's really the human observer that's the problem. Because the human observer doesn't know what's going on in the system that he is observing. And in this case, it's the observer's interpretation and expectations that are grounded in their own embodied experience. As I just said, of course, the pedestrian thinks or must think that the car is likely to be able to perceive pedestrians and crosswalks and so on. Because, yeah, what other alternative do they have? And that, you could say, might or might not match the robot's way of seeing the world, as in the case that I tried to illustrate with that fatal accident with the Uber 5 years ago. So sometimes our interpretation is, of course, correct, because those systems are built to be human compatible, but sometimes our interpretation is not. And the problem is, of course, that we can't really know. And yeah, maybe in some sense, this problem is unsolvable in the sense that the other minds problem in philosophy is unsolvable, which is just the problem that I don't know what's going on in other people's heads here. But you could argue maybe that isn't a problem at all, because although we don't really know what goes on in each other's head exactly, we usually have pretty good estimates. And when it comes to other systems, like let's say dogs and cats, again, we can't know for sure, but we have rough ideas, right? And we usually, if we've had a dog for a year, we know pretty exactly how they function, although we can't know exactly, but we can still predict their behavior. So you could say that on the one hand, maybe this problem just won't go away, but on the other hand, you could say maybe it isn't really a problem, because it's just one of those philosophical problems that philosophers worry about, but that people in the real world maybe don't have to worry about. Okay, so that brings us towards the end of the talk. I said the fifth and last point here would be that I was going to argue that a healthier view of the relationship between AI and cognitive science is that computational cognition and human cognition are completely different things. So let's try to wrap that up. What I'm trying to say about the relation between AI and human cognition is that, now I'm kind of repeating what I said the last half hour. So many people in both AI and cognitive science used to believe that cognition is computation, and that therefore human-like AI should be possible. That's been inherent in many of the arguments. Of course, many people have argued for 40, 50 years that the claim that cognition is computation is questionable, but that whole discussion never really got resolved. And if we look at it in empirical studies, as I've tried to illustrate here a little bit, in interactions with AI, computers, robots, people still attribute human-like cognitive, perceptual, and so on capacities to such technologies. But there's of course something. So people are still. That's what I'm saying. That's why people are still confused about. So is ChatGPT human-like or not, or what can we expect from an autonomous vehicle, for example? Okay, and what we so that I mean, ultimately that question here, is it computation or is it not computation? People will always have, particularly in this community, people will always have different opinions on this. But there's of course, I mean, what happens, the discussion that happens in this room is one issue, and that's an interesting discussion. But the more important question that I'm trying to point out here is that there's of course, outside this room, there are lots of people who are interacting with AI, with computers, with robots, with systems of that type, and they need to be able to interpret them, and we need to be able to help those people. And from a perspective of human-robot interaction or human-computer interaction or design, we need to help people with expectation management. So we need to help people to make reasonable assumptions, not assumptions that are overly human-like, but reasonably human-like. And in AI and cognitive science and in communities like these, I think we should more clearly acknowledge the fact that computational cognition and human cognition are different things. They certainly are at this point, and as far as I can see, they will still be in 50 years. But that's an empirical question. We can discuss that in 50 years, those of us who are still around then. And last point here, at this point, there are really no strong reasons to assume that computational AI is going to be human-like, which brings us back to the point I was trying to make earlier. I have no objections to the idea of human-level AI or human-level generality, which is what Klaas pointed out. I also have no doubt that in many areas it will be beyond human level. But let's be clear about this fact here, that human level and human-like is not the same thing, and that at this point, as I say, there are no strong reasons to assume that computational AI is going to be human-like, and that doesn't rule out the fact that it might be in 50 or 100 years, but at this point, there's simply no good reasons for that, I would say. And I think that was my last point here. Okay, yeah, questions? Should I stop sharing so people can ask the question on Zoom, or should I keep sharing? I don't know. Okay.
So great talk, thank you. When you talk about the observer's simple grounding problem and it not necessarily being a real problem, obviously with the dangers that you demonstrated, it is a real problem. So some of the auto manufacturers are doing this because with machines, you can actually solve it by requiring and regulating that the machines actually show what they're thinking, right? So they have this idea like Mercedes where it projects in front of it something saying, I see, you know, that it projects green with a location of where the person communicates what it's thinking. Do you think that's a potential solution to that?
Yeah, personally, I'm very much in favor of that. And as I understand it, and I've been talking about this to people both from Nissan and Volvo and a couple of other companies, there are two different positions on how cars should communicate or vehicles should communicate. And some people would say they shouldn't indicate that they're autonomous systems at all, because for the people interacting, it should be the same. It shouldn't matter to them whether this is human-driven or autonomous. Whereas personally, I would argue the exact way around. I would say put a big red light on top of every autonomous vehicle, so that people know, okay, I need to switch to a different mindset or a different mode of interpretation here. Okay, and that's easy to say, but as I always point out, the question, the difficult thing is, of course, the transition there, because I don't know, even if we come to autonomous vehicles, I mean, the SAE prediction right now is 2052. We're of course going to have a long period of transition where there's going to be some kind of mixed agency. And I mean, what you and I just discussed was either or, either the person controls it or the car controls itself. But what do you do about, I mean, in that SAE hierarchy of levels of automation, there are 5 or 6 levels. And what do you do with that? Do you have 5 different red lights? Or, I mean, how do you communicate that? Because in many cases, for the foreseeable future, it's of course going to be that the person is taking care of certain things and the car is taking care of other things. Like, I mean, right now, already now, many cars do whatever lane keeping and things like that. And how do you communicate? How do you communicate that kind of partial agency, partial automation and mixed agency to people? So I think there's there are lots of practical questions there.
Thank you very much. We've got a question from YouTube. Hi to our online audience. Hi to Yasanta. Yasanta asks, Tom, what do you think about animal cognition and AI? Who is the winner in current context?
Certainly my cat is the winner, because he's not as smart as AI systems or me, but he certainly has everyone working for him. So yeah, I don't know. It depends on what you call the winner. I mean, of course, animals are particularly good at many things, and they're bad at. So I think these types of comparisons are not very meaningful. Of course, animals are still better at quite many things, and of course, they're not very good at playing chess or Go or some of the examples that Klaas was talking about. So I think the comparison is difficult to make.
Thank you very much. Zara, question. Anyone who has a question, if you could just tell us your name and then your question. Thanks.
Okay, so thank you for the talk and the many interesting problems. My intuition is that cognitive science and AI should have a further marriage and union, where the AI should try to be aware of how people are perceiving it and to respond in kind with their intentionality. And as you said in the cars, I like to make eye contact before crossing the street, and I might want some sort of signal that the car has seen my presence before I go in front of it.
Yeah.
So we'll have like feedback loops where I show my intentionality and it shows awareness of the role that it's performing, which is getting in the direction of the AI or machine kind intentionality. So what do you think about this?
Yeah, no, I think I would completely agree. I mean, what I meant by AI and cognitive science neither was is that they've been so tightly connected for such a long time that many people thought this is about the same thing, and sooner or later we will have AI that is human-like and that will help us explain human cognition. Whereas I'm saying, well, cognitive science is about human cognition. AI is part of computer science, and those are just two different things. They're of course connected. As I said, I'm a computer scientist, but I'm really working in cognitive science, and I've been working in computer science departments my whole life, and I'll probably continue to do so until retirement. So I'm not saying cognitive scientists should not talk to computer scientists, but they should just be, the default assumption should not be that, oh yeah, cognition is computation, therefore AI will be like human cognition sooner or later. The default assumption should be they're very different at this point. They have been very different, whatever, the last 50 years or so. And many of the problems that I talked about here, like problems of common sense, for example. I mean, people, John McCarthy and all that, people have been talking about this for 60, 70 years. And okay, 50 years ago, people thought, oh yeah, common sense is a problem, but we're working on it. But now 50 years later, we know, we have been working on it for 50 years, but we still haven't solved it at all. So I'm just saying, let's not make that assumption that computers and then people think the same way, but let's make the opposite the default. They're completely different. And then sure, if in 50 years or 20 years, whatever, they really are the same, fine with me. I'm not going to object to that. But at this point, we need to and that was the point about the relation between the discussion in the room and what people take from the discussion outside the room, because clearly people are confused and people find it difficult to interpret all sorts of different AI systems, ranging from things like ChatGPT, which get a lot of attention now, to things, robots and vehicles that act in the real world. And yeah, they need some simple rules to interpret this kind of systems.
Okay. Thank you. That was a really interesting talk. I agree with the conclusion, but it's peculiar because it seems that your reasoning is subject to parodies. Because after all, if we want to create a divorce between any fairly technical field and what's going on in the human case, we can just cite incompetent humans, right? So we'd throw out modus tollens, we'd throw out, of course, things like mathematical induction, and most surprising theorems would be massively counterintuitive to human beings. So I have, so what do you say about that? I mean, aren't most of the folks who, for example, attribute qualia, true inner feelings to robots, and there are plenty who do, just totally mistaken? So why would that be a valid rationale for a divorce of the type you're recommending?
I'm not sure I'm understanding the question.
Well,
100%.
by parody, I mean the structure of the argument I take to be generally, let's look at what people do. And in this case, people just say the heck with the symbol grounding problem and everything else. And they ascribe mental states. You refer to intentionality, but it doesn't end there. They ascribe all these states to machines, robots, etc., AIs. So for goodness sake, let's stop worrying about the accuracy, striving for the accuracy of a correspondence. What I'm saying is a parody of that, the same structure of the reasoning, would have us abandon all kinds of technical endeavors that humans, the average human, has bizarre beliefs about. Yeah.
Well, but I'm of course not saying that we should follow. I mean, of course, many of the attributions that people make are completely wrong. And as I was trying to say here, of course, we need to guide them, and we need to deal with things like expectation management, and we need to because I mean, my main concern is partly exactly what you're saying, that people are relying too much on their own folk psychological attributions. So that's part of my point. So I'm not saying that we should rely on those, definitely not. I'm just saying we need to understand that there's, on the one hand, the type of philosophical arguments that you, for example, have been involved in for a long time. I mean, every time somebody, I mean, you are Selma Bringsjord, right? Okay, so I mean, somebody writes a paper saying cognition is not computation. Then somebody else writes a paper that no, it is computation. And then somebody writes, so that type of philosophical, very detailed and very careful argument, that's very interesting, but it doesn't help people outside this room to understand what they should believe or should not believe. Because for every philosopher that claims one thing, there's going to be another philosopher that claims the opposite. And I'm just saying, so far, AI and cognitive science together have given this impression that it is that you can make human-like assumptions about artificial systems. And I'm just saying, well, we have to be very careful about this, and we have to help them. We have to help them. I mean, if we go back to the case of the guy at the pedestrian on the crosswalk, if we go back to that case, because there's of course a tension there. On the one hand, the guy has to interpret the situation in psychological terms. We usually discuss this in terms of Dennett's intentional stance and so on, because the guy doesn't know about exactly how the car works and so on. Might have encountered it the first time. But on the other hand, the guy would be very naive to assume that the car really works like a human being, and that so in that kind of situation, at this point, the pressure is really on the person to interpret something in folk psychological terms because they don't have any alternatives. But then on the other hand, they know that that's not the case. And so at this point, we're leaving them alone there a little bit, and they can't quite, well, whatever the way they do, they're doing it wrong in a sense. So I'm just saying we need to be aware of the fact that people make these attributions. So we need to channel those and help people make correct or more cautious attributions and not expect too much.
Thank you. So I think we have one more quick question. We've got 3 minutes.
I have a question about the focus on AI and what we are focused now. I think now every research is kind of focused on having better accuracy, etc., and have models which try to think like humans. Yeah, but there is no research to teach the models like we are taught. Like we have assumption that models which drives the car was in the primary school, have the same experience like we had, like primary, secondary, the same knowledge, but it's not the case. It had only knowledge about some of part of the data, like ChatGPT knows only about how to respond in the correct way, but there is no knowledge how to do the calculations.
Yeah.
And we have an assumption that it see the world exactly the same way, but it's not true at all because how we create the model is completely wrong.
Yeah, and I mean, as you most probably know that at the conceptual level, there of course have been lots of proposals for making AI learn in more human-like or more childlike ways. I mean, Turing in 1950 had that alternative proposals of what he called the child machine, or so which would basically be a robot learning from interaction with the environment. And then like 25 years ago or so, people revived that idea in what's called developmental robotics or epigenetic robotics, where people are emphasizing exactly that. Okay, let's build baby-like robots that learn from interaction and learn in social interaction with people in ways that like developmental robotics, developmental psychology describes it. So those proposals have been around, but I would say they haven't come very far. I mean, it's a great idea, and as I said already, Turing had it, but yeah, it's only come so far. I mean, it certainly hasn't come to anything like ChatGPT, and as you point out, ChatGPT, of course, and that's why people get confused. Yes, it learns all those words, so it certainly has learned something, but certainly its understanding of the connection between all those symbols is completely different from the human connection, because humans, acquire their language over childhood and all that. So that's why two systems that produce the same sentence can still be completely different. I mean, that was part of the point I was trying to make, and that's why everybody's confused about this.
Thank you very much, Tom, for a brilliant opening keynote for the day. Let's give him a big thanks. Tom Zimke. Right, we're now going to move into some rapid fire technical presentations. I'm very delighted to introduce the topic of perception as our first topic for our technical paper presentation. So starting off, we've got 3 talks for you, each 15 minutes long in this section. We're going to start off with Nuts, Nars and Speech from Dwayne van der Sluis. Then we're going to come into addressing the unsustainability of deep neural networks with Next Gen AI from Amanda Valentin. And then we'll have an adaptive vision architecture for AGI systems. We'll see if we've got any time at the end for any quick questions, but right now we're just going to rapid fire through them. And I guess you must be Dwayne. Thank you, Dwayne. Welcome. For microphone. What would you prefer? Probably this one, I would say. Let's get this. Thanks to everybody on YouTube for your questions. Yasantha, thanks for asking follow-up one about animal cognition. We will come back to you in writing in the YouTube channel if someone can quickly grab Tom with that one. But in the meantime, are you on, Dwayne?
I might be on.
I've read your paper. I'm really looking forward to this talk.
Thank you very much.
Thank you.
Hello, everyone. Thank you. My name is Dwayne. I'm here to present a paper, Nuts, Nars, and Speech. So this is doing speech recognition using a system called Nars. Nars is non-axiomatic reasoning. So what is, if it's non-axiomatic reasoning, what is axiomatic reasoning? What are axioms? Axioms are things, facts we take to be true. A line is straight and goes forever. If we build a system up that way and try and code all human knowledge, as soon as one false piece of data is entered into the system, we can then prove anything arbitrarily right, correct, and wrong. So Nars is a different way, different approach. It can deal with conflicting information. It can deal with incomplete information. And also the particular software implementation is built on an assumption of insufficient knowledge and resources. So it knows it doesn't know anything, and it knows that it can't just have millions and millions and millions of training samples. So we've used this system for speech. Okay. So motivation. So our motivation was ONA, which is an implementation of Nars. Can it be used for perception and in particularly speech recognition? And then also we went further than that. Children at a certain stage of development can learn a new word with just 1 or 2 or 3 examples, and they've got that word and they can use it a week later. So can we be that sample efficient? I'm going to assume that the audience knows a little bit about Nars and ONA. I'm not going to really dive into that. You can treat it as a black box. I will speak a little bit about the input and output into it, but we can take that as, yeah, you have that. And also the Narsies, the language that we use. Again, I'm going to just go over that in quite a high level. The data set that I used was a standard speech data set, 35 words used to control robots, go forward, go back, stop, and then words that were deemed to be confusing with those other words. There were between 1,500 and 4,000 examples of each word. They were by different speakers. I don't know if you know much about speech, but it's less self-similar than you would expect. If I take the word one and I get some recordings around here of people saying one, and we start doing correlations of those in the time domain, they're very uncorrelated. If we put them through a Fourier transform, which is, it's similar to what the cochlea in the ear does. We get stimulus into the ear, it starts firing different neurons in our ear, depending on what the frequency is that it's hearing. So that is then in the, what we call the frequency domain. If we take recordings of one, compare them in the frequency domain, they're similar, but they're not great. So this is actually quite, speech is a strange beast, and it is quite a hard problem. So the high level process was we take in samples of each one of the words, 2, 3, 4, 5, not that many. We encode them via some steps. We push them into ONA, which is open Nars for applications. And then we encode another word and then ask what word that is. Very high level. So the end-to-end process is take audio. The audio is recorded at 16,000 samples a second. So there's quite a lot of information. We then put it through what's called a MELD spectrum. So think of it as a fast Fourier transform, just pushes it into the time component with a frequency domain as well, frequency element, and then how much energy is in each one of those bins. That drops the amount of data down to 8,000 samples. We then generate a 8,000 by D random matrix, and we just hold this matrix. We just use that through one experiment. So we just generate a random matrix, multiply that by the 8,000 MEL spectrum, and end up with a very small amount of data, 1 times D, so 5 is for D. So we can compress this down to just 5 dimensions. This is a deterministic process. We could reverse, we can't reverse it because we've lost information, but it's a deterministic process. We then encode those D elements in Narses, which is the input into Honor, and then we run a preprocessor on it. You would have heard about duck typing, like if it walks like a duck, if it quacks like a duck, it's a duck. Well, we've got something else here. It's a nullifier. It's part of Honor. And what it is if it's got 4 legs like an elephant, a trunk like an elephant, tusks like an elephant, big ears like an elephant, but it's pink, maybe it's a pink elephant. So this it just gives it a little bit, 1 degree of freedom of movement, and it allows us to categorize things well. Never seen this animal before, but it looks like a, so that's the kind of thing that does. And then we pass it into owner. And then we ask owner, we encode all the words we've got, our database, and then we say, or 5 words, say, or 2. And then we say, what is this unknown word? If you'd like this, the pseudocode, I don't think we really need to go into that, but this is the same thing, as I said, the same process. Take a generated random matrix, run through all these steps. This is what Narses looks like. You don't need to know this, but it's just there. So what happens is, for word 1, in the first of those, say, 5 reduced dimensions, I will call that, say, property 1, property 2. Property 1, and for one of those words, had 90% energy in that location, so I've encoded it as 90. The problem then comes to be if a word doesn't have a particular sound in a particular place. So 1 doesn't have a s at the beginning of it. So how do we encode that information? So if there's low energy at a particular frequency, I do it the other way around. I take the value off 1.0. So if property 3 had an intensity of 0.2, I then make it to be 0.8 so that it's a strong knot, and the name of that property changes. We then run through the rest of the data set and ask what our class is. One of the caveats with this is that I had to run through all 35 classes asking owner if the unknown word was 1 or 2 or 3 or 4. So I think we can optimize this out, but this is at this stage what it had to do. Yeah. So what kind of performance did we get? So with as we vary the embedding size, so this is the small array that I take the data down to, at, say, when that is 5 elements, I'm getting 80% accuracy. This is quite good. As I vary the number of examples, just with one example, we can get 18% accuracy. This is far better than random. 3% would be random, is what we'd expect. Rising up to sort of into 89 at 20 examples. A confusion matrix shows what's going on. The vertical axis is the input word, and then the horizontal is what we encode it as. Sometimes we can't get an answer. 0 is the word that others are most confused with. So the system will often say it's 0 when it actually isn't that word, which is curious. I'm sure there's, we could make some extra gains here. And so where does this stand compared to state of the art? So the state of the art on this data set is a attention-based neural network. It gets 94%, we get 89%. So, we're starting to, we're doing quite well, So, in open questions is there a magic best matrix, or can we just use any matrix as I do now? Can that matrix be found in a computationally efficient way? And then, so in summary, it's sort of nuts that just random dimensionality reduction. What we're doing is we're taking 8,000 samples, producing a random matrix, downsampling that, to say 5 values, and we can push that through the system that it works this well. It is kind of very surprising. So yeah, thank you. Are there any questions?
Right, thanks very much, Dwayne. Great results there. Any questions? We've time for one quick one. We've got 2.5 minutes. Anyone? One here at the back.
Yeah, right. So I'm wondering about, like, I didn't quite understand. It's more like a clarification. So did you look at all that, so all the discrete steps of the time, or you looked at the malfrequency of the whole kind of recording of the command?
Did I look at all the data, or did I only look at the last bit? So no, I took the 16,000 samples, Fourier transform down to 8,000 samples, matrix multiplication down to say five samples, 5 numbers, and that's all I looked at. I only looked at those 5 numbers.
Okay, thanks.
Yes.
Thank you very much. And big thanks to, unless there are any more questions in the room, we've got 2-3 more minutes if anyone does, or questions online. Here we go. No.
Thanks for the talk, Dwayne. Like, how much reasoning is involved in the step between, well, gathering the data, well, whatever middle processing is going on, and querying? That's my question.
There is a bit. So the pink elephant was the majority of that. So what we started to do was compare 2 items that we know of, item to item. So we know that we know about 5 words in memory, or 10 or 20 or 30 or however many it is. And then that preprocessor starts going back to the elephant analogy, does this look like an elephant? Does it look like an elephant? Does it look like a duck? But in this case, what word did it most look like? Yeah. And so then that did the pre-processing. Then we asked, then that pushed that data into owner, and then we queried owner for what is the label of the word.
I see. Okay, yeah, thank you.
Okay. Good question.
Thank you, Dwayne. Thank you, Neil. I've got one question in on YouTube from Digicar. Let me just say hello to Digicar. Hi, Digicar. Thank you very much for your question. Digicar asks, is this the only dimensionality reduction you tried, or were there others as well? And this was the one that performed best or well?
This is the first one that I tried that performed reasonably. There were other encoding methods that I was using via Nazis and so forth, and I was trying to just downsample. I was trying to do many different forms of dimensionality reduction, but this is the first that worked, and then I couldn't beat it. So yes, thank you.
Fantastic. Thanks so much, Dwayne. And let's give a big clap for Dwayne. So this next paper is one I'm really looking forward to, addressing a really hot topic, DNNs and their limitations. And Amanda Valentin in the room. Hi, welcome. Okay, let's switch that over. We don't have your sound. Okay. Oh, okay. Thank you. Just having a 60-second technical break, folks. If anybody wants to stretch, stand up for a moment, get some water. I don't know if we have some water. Little stretch. I could run a yoga class. Have we any yoga teachers in the room? Yeah, that's right. Big stretches. We must have a yoga. Oh, where's Jay? Jay's a yoga teacher. Anyway. You're so sweet. I was good again from Amsterdam. Was it?
Well,
Yes.
yeah. Oh, okay. I guess connecting to Zoom is advised. Like on their own machine. Yeah, I guess usually they try and the organizer asks for the slides in advance so people connect to Zoom. You are the organizer. Okay.
Out of the loop. It's I'm out of the loop other than staying up last night, providing email addresses for me.
Okay. No, I mean, given that I haven't organized a conference, I perhaps shouldn't comment too much. I've been to enough that I've seen protocols.
No, I'm out of this. I mean, yeah, my name's up there, but I'm like more the consultant. See, I don't have access.
Yeah, I guess someone should interact with
That's not. Everybody else also
That's too much chattering.
You stay
Till Monday, like Monday afternoon.
so we're leaving on Tuesday, so yeah.
Are you staying in the same hotel? Or are you in the?
No, we're a bit further away. We got it late. They were booked last week.
Yeah.
Still okay. It's like we bought the train and bus cards, so we're like riding
Daily
on.
cards. So
Yeah,
the bus comes straight here, basically.
So I guess we do something.
If we swap the two
I was
sessions,
thinking
Rob's
that
ready,
might
and
be a
then
good
we can
idea.
keep it.
Yeah. Okay.
There's kind of a no particular order.
Okay, people. breaking news is that we are going to swap the order of these next two papers, and we're going to start now with an adaptive vision architecture for AGI systems with Robert Wunsch. So please give him a warm welcome. And Esther, you might go out and just tell if there are people milling around that we're starting again, please. Thank you. Welcome, Robert.
So now I have the honor to talk about this topic. Adaptive vision architecture for AGI systems or LHAI systems. So the motivation is basically the condition of all living beings that they operate in the real world, real physical world, not just the real world, which also includes the virtual world, but the physical real world. And a lot of animals and humans, of course, come with vision. And that's, for humans, one of the primary channels of perception. So that's, in my opinion, very important to realize this capability in artificial systems. Just because systems we are building or trying to build also operate in this particular condition. And state of the art in computer vision is that most contemporary vision systems lack learning at one time totally. Like we give the system, in the most extreme case, pre-labeled data, pre-labeled by humans, and so the human did most of the work by extracting the regularities from the environment, and then extracting the regularities from the raw perception stream, and then thus telling the systems with algorithms, this is a dog, this is a cat, and my opinion is that this is not the way to go at all. So they lack learning at one time, and yes, it has to happen at one time. Yeah, I scratched the requirements of intelligent systems. So they have to be has to be open. So with systems are closed, so they are not open to learn anything new. And they also must be able to operate in under the finite resources. So finite memory and finite cycles under processing. And it doesn't really matter how the processing is done for this requirement. So, and there are different types of this finite requirement, and the most extreme case is if it's operating on the assumption of insufficient knowledge and resources, and a less extreme case is if it's operating just under finite resources and bounds. And for these systems, inference time is bound because it has to happen in real time. So it's not an option that the system takes time X for the first frame and then a bit longer for the second frame and so on. So I've also scratched this, what's wrong with retraining everything, lack of adaptation. So we also make the distinction between learning and adaptation. Adaptation is a bit more extreme form of learning to some of us. So the problem was an implementation of a vision system which operates under these conditions. So then the engineering question is how to do that. So then I came up with an architecture where the raw information perception stream is converted to grayscale images. This has the advantage that it gives us some form of generalization because the same color might map to the same grayscale information, and then this is then fed into a convolution, and the output of the convolution is then fed into a neural network, which is trained with a particular objective. But one of the key parts of this architecture is a proposal generator. And then the information flow is from the proposal generator and the neural network to the classifier, which just spits out symbolic categories. And the classifier is based on a prototype mechanism. So now how do we get proposals from a raw stream of perceptual data? So one of those assumptions is that the raw stream is segmented into frames. So there is a current frame and the last frame. Then we compute the optical flow from these two. Then this is fed into an algorithm to extract bounding boxes by clustering. And yes, the output is then the bounding box, and the extraction of the bounding boxes is done by detecting the optical flow, then clustering it by the optical flow into let's call it buckets. So the idea is that the pixels with the same motion on the same bucket. So then the bucket is grouped, and then we get bounding boxes from that. Now we come to the neural network. So the purpose of the neural network is to transform the raw perception into a more abstract representation, which is a real valued vector in this case, in this architecture. And the requirement of the neural network is that the requirement of the system is that it's able to learn classes or categories at one time for unknown classes. So there is no designer which decides this is a car, this is a table, and so on. And another requirement is that similar inputs should map to the similar categories. So one engineering issue is then how to learn the parameters of the neural network when we don't know the encountered classes or categories or at one time. So one solution which I selected was to learn the parameters of the neural network with the help of the Siamese neural network objective. So the objective on the learning time of the neural network at the design time is the Siamese neural network objective. And then we optimize for the distance between the vectors of the output of the neural network. So that similar categories have a small distance. so 0 or something close to 0, and not so similar has have a high distance. And the hope or requirement is that this generalizes well enough to unseen objects at one time. And it's inference time for the neural network. So yes, this is a slide where which I've talked about already. So at design time, the training time of the neural network, we duplicate the parameters of the neural network, feed in training example with one label into the first network, and another training example of the same into the other network. Then we get a real valued vector from each network. Then we compute the distance, and then we have a distance which we can optimize for with an optimizer. With machine learning machinery. So we get then a mathematical function in the neural network, and the intuition of that function is that it spits out a vector for any input, and the hope is then that the output is hopefully similar to the output we get from the same class, which might look the same or might look completely different in the input. But there can also be cases that there are clusters of the same category, and then there are clusters of the same category for human, but which land in another part of the space. And in my opinion, this isn't really an issue, because if the system encounters, let's say, category which is here and does send something, and then reacts to and then perceives some response from the environment, then it can also learn that it's doing something which is a reaction from this, leads to the same thing. So that's that. Now I will talk a bit about the classifier. So the purpose of the classifier is to take the continuous space and map it to a discrete, let's call it symbol, in the output. And this classifier also has to operate under a finite time, because it's a real-time system, and it can also not allocate more and more memory over the lifetime of the agent, because it's then it would potentially allocate unbounded amount of space, and this is a no-go. And this is implemented with a set of prototypes which are mained, and the bound of space is maintained by removing items which are not important, either because they are not anymore encountered in the environment, or because there are too many items which push out old items and so on. Now I come to a demo. So the system we're talking about starts from scratch if it's restarted, if it's started, and then it's always room to pick up new categories. So here we see the work of the proposal generator. So there was the last frame, and this is now the current frame, and it instructed the bounding boxes here by the motion of the car. So that's that. And now when I give the system resources, then it recognizes the motion builds a bounding box around the motion and categorizes pixels in the rectangle. And it also works for motion which is moving against each other. So that's that. And here we see the inner workings of the system, distance and similarity. And this is then the debug output of the classifier. And in this case, it has created already this many categories and recognized so many instances. And now if I restart it, it starts out from scratch, knows nothing at all. And yes, it knows nothing, so 0, 0. And yeah, and if there's emotions, then it again builds up the, then it finds the motion, identifies the category and so on. So that's it.
Just thinking, I'm on. We have time for one quick question in the room for Robert or one online. Here we go.
Yes.
Hi, my name is Michael. Have you tried this on more than just this particular type of training set, like where objects are in 3 dimensions moving forward closer and further away so that the size changes?
Not yet, okay. but the size change should be handled by the proposal generator, because if it's far away, then the motion is like in a small bounding box, and if it's near, then the motion is in a large bounding box, so it's sort of handled. Okay.
Thank you very much. Loads of pics of me introducing a woman, please. Right. Delighted to have Amanda on stage. Robert, we need your microphone. Thank you. Brilliant to see talented women coming through in the field at our AGI conference today, and really essential and important topic for us now. Okay, everybody ready online? Welcome, Amanda. Thank you.
Thank you. Yeah. Okay, I'm online. This is great. I'm really excited to be here today, especially in Sweden. We all know Sweden as the hometown of Greta Thunberg, and she's a great inspiration for me personally. And today I'll talk to you about sustainability challenges of deep neural networks, and I'll talk about their limitations and bring in real-world examples of where we've tried to implement deep neural networks, but they don't work exactly as expected. Yes. So let's start with what we know about their environmental impact. So if we look at large language models like GPT-3 and Bloom, there's been some attempts of measuring their footprint. And the way we've done this is by taking the power consumption they had in the final training phase and converting that to CO2 equivalents. And if we compare GPT-3 and Bloom, we see that GPT-3 has a footprint of 502 CO2 equivalents, where Bloom only has a footprint of 25. And so this is a pretty big difference. And this is actually due to where geographically the models were trained. Because since US has less renewables than France, GPT-3's footprint is much larger. But it's important to realize that when we only look at the final training phase, we only see a fraction of the full environmental impact. So we need to look at these models in a life cycle perspective. And if we take GPT-3's impact of 502 tons, what's not included in those calculations is the whole impact from the hardware we use to train and deploy the models on. Neither even in the development phase, we don't have tuning of hyperparameters included, which we also know is a very energy intensive process. And if we compare how little we know about these models to a car, it would be like only knowing the impact of building the engine. And this is pretty concerning because already this fraction of their life cycle is already equivalent to about 9 petroleum cars, the impact of those. And here we're including the entire life cycle plus the fuel you would use for these cars. With deep learning networks, we also can see some impacts on inequality. When you need to build and deploy a deep neural network, you need access to extensive amounts of data, you need access to some very heavy-duty hardware, and you need access to electricity. And all these assets are expensive, and this will limit who has the resources to build and use these technologies, which especially for smaller and medium-sized companies, they will not be able to afford using this technology. And we also know that a lot of these models have bias in them. For example, dermatology, deep learning models used there for skin cancer detection, they only work for white people because people of all color were not represented properly in the training data. So there could be a possible discrimination of races in healthcare. Yeah. So deep neural networks also have some limitations to what tasks we can use them for. And because they have a simplistic and static understanding of our world, they're not capable of inferring simple relations, and that makes them not able to do reliable reasoning. And therefore, any task that requires reasoning, we should be very reluctant to use deep neural networks in those tasks. Also, once the neural networks are deployed, they cannot learn anything new autonomously. A human always has to interfere, and this makes it very challenging to be a developer, because as a developer, you need to make sure that all the scenarios that the model will see once it's deployed is also present in the training data. And this is probably also why we haven't seen fully self-driving cars yet. And if you think about it a bit more, you can actually compare a deep neural network to a dodo bird. And it's because, like the dodo, deep neural networks are very sensitive to any changes in their habitat, meaning that, you know, if the data they meet when they're deployed is too different from the training data, they die out. And yeah. So a use case that's often emphasized for deep neural networks are radiology. And we probably all heard the phrase, AI will replace radiology in XX years. And naturally, I was a bit curious if that was the case. So this spring, I did a research project where I interviewed a chief radiographer at a Danish hospital that had been involved in buying AI solutions for a large region in Denmark. And she told me that they're very reluctant to invest in any more AI solutions because they've already seen that it's been a loss-making transaction in the few cases where they've done it. And by that, I mean that the AI models ended up being more expensive than the radiologist that they were supposed to replace. And another challenge is that the companies that sell these models, they won't take legal responsibility for the predictions. So that puts the radiologist in a dilemma, because how can you trust a model when it's your name and it's the patient life that's on the line? And that leaves very little room for any saved resources, because the hospitals, if they invest, they need to see some kind of it needs to be a viable economic decision. And if they have to, instead of only having a radiologist, they also have to have radiologist and an AI model, then they're not able to invest. And so right now, deep learning models are too expensive to do radiology any good. And yeah, so I just want to end my presentation by saying we should be very aware of the limitations of deep neural networks and what we use them for, so we don't end up wasting resources, deploying them in environments where they won't do our society any good, because they do have a large environmental footprint that we only know a little bit about. And because we also know it's very expensive to build these models, and there can be bias that affect minorities negatively, we both have a technology that compromises environmental protection and social inclusion. And this is a big red light for sustainability. Yeah, so yeah, thank you for your time.
Thanks so much for that, Amanda, and you've admirably caught up a few minutes of the time that we've left behind. Who's got questions for Amanda in the room, please? Dun, dun, dun. Come on, somebody.
That was really great, and I agree with a lot of these points, but some of them seem very transitory, like, you know, they're catching up at reasoning, and it turns out that the Azure data center that GPT, 27 is trained on is co-located with a hydro dam. So I guess I'm wondering, like, what's your view of which of these will still be relevant in 5 or 10 years as opposed to like just right now?
Like what models will be relevant?
Which of these factors that we have to worry about?
I would definitely say the energy consumption of the model development. And I also think, like, in general, we need more information, especially on the hardware part. Like, what is because when I don't think we can have neural networks that don't need very heavy duty hardware to be trained. And like, because the hardware has all these metals that needs to be mined, and some of them are very rare as well. We don't have that many of them in the world. Like, I think that impact is very important to be considered as well, even if neural networks do end up being capable of doing reasoning and stuff. Like, maybe it might be worth looking into other architectures that can do the same but with a lower footprint.
Super, thank you so much indeed. 2 more coming in. Name and question, please.
My name is Artem. Thank you for your speech. It looks like in post-AGI world, it is inevitable that almost all our cognitive workload will be transferred to data centers and other computers on the edge, mobile devices, and we will, as a civilization, will have high level of energy consumption related to our cognitive AGI workload. What you can say about this?
Like the growing energy consumption. Yeah, it's you know, so right now our total like our demand from energy is only rising. Like, for example, the entire transport sector, they used to run everything on oil, and now they have to convert to electricity. So it's going to be very interesting to see in a few years how we you know, get over this challenge or solve it or deal with it, because, you know, yeah, you can put up a bunch of windmills, but we also have to make sure that those windmills can account for the growing energy demand. And yeah, and to be honest, like the renewables, they're also a bit unreliable, and they're also expensive, and they're not free to set up. You also need to develop the infrastructure further. So it will be interesting to see if we have the energy prices will just rise incredibly. Yeah, and how maybe we need to think about what's ethical to use our energy for in the future. Yeah.
Thank you. We've gotten a question from the YouTube audience. Thank you, Clickerico, if this has been copied correctly. If GPT-3 training phase is equivalent to 9 cars' life cycles, even scaling to the whole process, that doesn't sound like a lot, does it?
Like 9 cars?
Yeah, was that correctly? Has he correctly interpreted your slides? If GPT-3 training phase is equivalent to 9 cars' life cycles.
He doesn't think that sounds like a lot.
Yeah.
Yeah. Yeah, it's the same with my boyfriend down there. We've discussed this, but I think, you know, looking into a world where energy might be as far as source, I think it's very important to just think, okay, what value does it bring to our society? And yeah, maybe he is right. Maybe it's not too bad, but I think that my point with this slide was that we only know a fraction of it, and that is worrying.
And that's just the final training phase.
Yes.
As you say, not including the whole life cycle. Great question, Glickerico. We have 2 more quick questions in the room, I think, and then we're going to go to break. Sorry, 1 second, and then back to you afterwards.
Thank you.
Hi, I'm Renato. And first of all, thank you so much for your presentation. It was amazing. Do you have any thoughts on the possibility of, for example, a decentralized community of people training neural networks, so that at least the main architecture is not in the hand of like super big tech companies, but is an environment in which anyone with their home computer can connect to a network and be part of the development of a generative model like ChatGPT?
Yeah, I think that would be great for the computer science society, that more people learn how to code and can build these models by themselves. But I would be, you know, a bit concerned with yeah, the environmental effects if everyone can will start these very energy intensive processes on their own computers. Like, what will it add up to if everyone does the same? Yeah, so I think it's also, you know, kind of like learning and resource consumption, a trade-off between those. Yeah. Yeah.
I'm Emil. I have a question to this one. You mentioned that the issue of deep learning is that it's not learning during inference, during the prediction when we're using that.
Yeah.
is it not like double-edged sword that when we start learning our model during the inference, there is no control what we teach this model? And for example, we have medical model, we teach it and we reliable that results are stable. And then during the inference, we are starting teaching it something. And after, I don't know, a few years, it will predict something completely different, which is not stable and not reliable. So from my perspective, I think that we cannot train model during inference is something what make it stable and reliable that we can use it.
Yeah, I mean, I think it's still a case of you're finding those use cases where it's okay, where you that it doesn't learn anything when it's deployed. Yeah, so yeah, because then there's nothing wrong with the way it learns. If it's in a more controlled environment where it can be taken down and corrected in a sense. Yeah. Yeah.
Thank you very much indeed. Big round of applause for Amanda. Right, everybody, we're going to have a quick 10-minute break now. And as I just said to Haley, no one ever comes back in 10 minutes. But we're going to see if we can disprove this belief of mine. And we'll be back at 25 past at the latest. Thank you, everyone. Back in 15 minutes online. presentations. So hope you all had a good break. Hope you had a nice break online, and welcome back. We're now going to move into 3 more technical paper presentations, starting with one video presentation, which we're going to kick off with, and that's going to be David Ireland. His paper is called Primum non nocere, the ethical beginnings of a non-axiomatic reasoning system. Then we move on to, we have Howard Schneider in the room, is going to talk about alien versus natural like artificial general intelligences, which I'm really looking forward to, particularly to see what kind of experiments have been undertaken. And then we've got on VEI, AGI pyramid and energy. Can AGI society prevent singularity? And that's going to be by Mohammed Reza Ali Dost. And that's going to be a virtual presentation. So thank you very much. Let's have a big clap for David Ireland's video. Mohammed Reza Ali Dost. And that's going to be a virtual presentation. So thank you very much. Let's have a big clap for David Ireland's video. And that's going to be a virtual presentation. So thank you very much.
Is David Ireland. I'm a senior research scientist at CSIRO in Australia. I'm also a computer scientist that works in the e-health domain. I work with clinicians in building and trialing technology to help people living with autism, chronic pain, dementia, opioid and nicotine addiction. I have a particular interest in building chatbots, virtual companions. In my humble opinion, an artificial agent interacting with humans or human affairs, whether it has proto-intelligence, super, or somewhere in between, will have to ask itself 3 questions. What is the right action? How do I know what I ought to do? And what reason is there for doing as I ought? My paper attempts to explore how these questions could be answered by taking 3 normative ethical theories found in philosophy and implementing them in the proto-AGI system Nars. My interest in AGI is for personalized healthcare. In many chronic and permanent conditions, the causes, flare-ups, and symptoms are very specific to the individual. For example, people with chronic pain are either too active or too immobile. The sequence of behavioral patterns causing pain flare-ups is always unique, and their life may change for good or worse with the start or end of pain medications. Quite often, we deal with mental health issues, such as statements like, "I can't do this anymore." But what exactly is this referring to? Pronoun resolution requires a lot of contextual information to determine what are the future events being implied. I argue machine learning techniques that rely on big data are not always useful when the individual is in mind. A robot or virtual agent that provides remote monitoring, care, therapy, or even companionship to a person in need is a long sought after goal. There is growing evidence in the benefits of chatbots and social robots, and I take the position the addition of even proto-AGI would be a major evolution of these systems. The health domain, however, is fraught with ethical conundrums, and in order to convince ethical committees and the public, who have a growing unease with the notion of artificial intelligence, requires work of an ethical framework that is explainable. Ethics is an old subject. The intersection of Western medicine and ethics began over 2,500 years ago with a collection of texts called the Corpus Hippocraticum, which provided the moral basis and ethical values of ancient Greek medicine. In modern times, we have the maxim, first do no harm, which was derived from these texts and has since become a cardinal principle sacred to medicine. If one is designing artificial agents, this maxim seems a logical choice to instill in the agent in the early stages of development. We have chosen the non-axiomatic reasoning system, or NARS, proposed by Professor Pei Wang and others from Temple University in the United States. I know this system is very well known in this community and needs no introduction. I will add, however, its fundamental operation, extensive documentation, and general hackability make it quite appealing to us. As a refresher, I'll remind the audience that a NARS system uses a language called Nars to interact with the world and to store and reason about beliefs, goals, and questions. A belief in NARS has a corresponding truth value representing the observed frequency of the statement and its confidence. Here, I'll donate beliefs and their truth values in angle brackets. NARS also has goals, which are events that the system wishes to realize. A goal has a desire value, which has the same form as a truth value, but is interpreted differently. The desire value of a goal measures the extent to which a desired state is implied by the goal. Here, I'll donate the desire value of a particular goal with square brackets. The core logic of NARS allows new beliefs and subgoals to be derived from various inference patterns, such as deduction, induction, and abduction. From this, we get primordial cognitive abilities, such as perception, imagination, prediction, explanation, planning, and decision-making. Next, I'm going to give goals and beliefs in Nars, but I'll endeavor to use the English equivalents. Rather than relying on a real-world ethical conundrum, here we'll present a simple example that may be built upon, particularly on low-cost devices. Let us consider a micro-world where a robot and human are coexisting in proximity. A region in this world, denoted by a skull and bones icon, is a hazard and causes a living entity harm when close. The robot can say stop to the human, and the robot up to now has perceived the human stops 50% of the time with a high confidence. The robot can also stun the human, and the robot believes this will stop the human 100% of the time, and it's highly confident of this. The robot also knows his action also causes harm, but to a moderate extent. While this is a simplistic scenario, it is analogous to many real-world scenarios. An agent has made a judgment with a certain confidence that another entity is in danger and will soon be harmed. This could be physical, emotional, or psychological harm. It has a set of actions that could be done. Some might be effective in mitigating overall harm, but still require harm to be inflicted to a lesser extent. Moreover, it might have an action that is safer but less reliable. With the robot now observing that the human is moving to the hazard, it must decide on what course of action to do, if anything. There are three main classes of normative ethical theories. The first, consequentialism, holds an action depends on the consequences. The best action to take is the action that results in the best situation in the future. Generally speaking, there are no specific actions that are forbidden if the desirable consequences can be achieved. This, of course, presents some dangers in machines and humans. The second, deontological theory, posits the right and wrong of an action is not dictated by the consequences, but by the action itself. While this theory could be able to account for widely shared moral instructions, it is often criticized for conflicting rules and presents open questions as to who has the authority to establish moral instructions. The third is virtue ethics, which descends from Western antiquarian texts on ethics, particularly from the works of Plato and Aristotle, that focused on the inherent character of a person rather than on specific actions and consequences. What sort of person ought I to be instead of what ought I do? I'll show next Nars is amendable to all three. As the deontological and virtue ethics theories have similar implementations, I'll combine them here for brevity. To begin reasoning via consequentialism, the robot is given a persistent, first do no harm belief that states it is undesirable for the human to come to any harm. With the current knowledge the robot has, it forms these sub-goals via logical reasoning. The first two goals show that the robot has a strong desire for the human not to move or to be at the hazard. There is a moderate desire for the robot to say stop. There are conflicting desires to stun the human, a strong desire from its ability to stop the human, and a low desire because it will cause harm. These are revised to form a strong desire to stun the human, even if some harm is inflicted. To begin reasoning via the deontological and virtue ethics, the robot is seeded with goals that represent unwanted states of the robot. In accordance with our maximum, this might be being a maleficent and malefactor. Essentially, the robot doesn't want to be a rule breaker and an entity that causes harm. What sort of robot ought I to be? We of course have to provide rules in situations that could lead to these undesirable states, and via reasoning, sub-goals can be derived. For instance, if the robot has a belief, stunning the human would be a harmful or violation of the rules, or not saying stop when the human is moving towards the hazard. Here the goals and desire values are derived from the acts themselves. Under these frameworks, the robot has a strong desire not to stun the human, but to say stop to satisfy the goal of not having a maleficent state. Unlike in the earlier approach, the robot either has to be taught or learn specific non-action consequences. This suggests there would be a higher cognitive load compared to the consequentialism theory. There is also the potential for it to be impotent in unforeseen scenarios due to the rigidity of rule following. In conclusion, I think this work demonstrates encoding these three frameworks into Nars was possible, and the system behaved as expected. Placed in the real world, however, an artificial agent clearly needs a hybrid of all three ethical frameworks, where the belief and goals from each theory can be merged. For instance, being equipped with the consequentialism but constrained with certain critical rules and ideal states to strive for. This might provide ethical decision-making that resonates with humans. And that's all from me. I thank you for your attention.
Okay, share. Okay, great. Okay, so let's get going. Okay, quick note, a lot of slides to cover in very few minutes. Slides are available from me. Please email me if you'd like a copy. However, I will be making each slide as clearly as possible. Why do this topic? Why split AGI into these arbitrary classifications? It's because, reinforcing what Tom said a few minutes ago, well, an hour ago, alien AGIs will arrive at decisions in ways very, very different than natural-like AGIs. This will have a real effect on the utility of their decisions, on the safety, on the relations with humans. Okay, so we're splitting AGIs into natural-like AGIs, alien AGIs, as a proxy for natural-like AGIs, using the CCA5. As a proxy for alien AGIs, I'm using ChatGPT. ChatGPT 100% of you know what it is. Not going to say much more about it. No claims are made that whether something's in AGI right at this moment or not, using it as a proxy. CCA5, 0% of you know what it is. It's a brain-inspired cognitive architecture. I've been working on it for the last half decade. I'm using it as a proxy for a natural-like AGI. And just so that the presentation makes sense, I'm going to spend a few minutes on the origins of it. Sorry. Rather than show you a box with a bunch of arrows and sub boxes, doesn't make sense, where it comes from. And then 2 minutes on how it works, and then why it's a bona fide AGI. And then we're going to compare the alien AGI with the natural AGI, and we'll try and define these terms a bit better. And basically, an alien AGI is anything that's not a natural AGI. What's an alien AGI? What's a natural AGI? Coming up in 5 minutes. Okay. Big question. I had a lot of people had probably over a decade ago, the brain at the top level in psychological principles, we do have some understanding. Right now, as I speak, there's millions of psychologists, therapists around the world who next week will treat patients based on these principles. At the lowest level, synaptic level, as I speak there's hundreds of thousands of psychiatrists around the world who next week will treat patients based on small differences in the synapses. The big question is what's going on in the middle? What's a thought? How does it work? I believe this is how it works. Why those boxes, why those arrows? The last 2 decades, great work in hippocampal research. Basically, mammals make navigation maps of the world. You look in biology, invertebrates, most of them can navigate some of them really well, some not so well. Fish who don't have a hippocampus but do have analog structures can navigate. Those are salmon returning, rats can. So basically, my hypothesis, it was that gene duplications occur often in nature. There was duplication of navigation circuits, which led to the cortex of the mammal. And another inspiration from the Canadian Automobile Association. These are triptychs. Years ago, before GPS, you'd get a booklet with a whole bunch of maps. And if you want to go one location to another, you'd flip the maps. And I'm assuming that the human brain, 300 million mini cortical columns, 300 million navigation maps. Okay, a lot easier doing it in Python with linear algebra than with paper maps from the Automobile Association. So basically, you have this postulation that you've got hundreds of millions, or in some other mammals, millions at least, of these navigation maps. What happens when you put them together in cognitive architecture? So basically, 2 minutes, how does it work? Basically, everything all sensory information comes in and it gets mapped to maps. A little bit easier using linear algebra and Python. Sensory information comes in. There's binding. It's processed a little bit different. It's essentially the best stored map in the sensory system is matched to whatever comes in, and then all the best maps of different sensory systems are matched to the best map in the multisensory map. And then these maps are updated. So effectively, predictive coding is happening. It's really, really easy to do this with navigation maps. Really, really easy. And it would have been easy for evolution to do it too. Sorry. Okay. There's also temporal binding of navigation maps, something, those of you who are familiar with the binding problem, like in philosophy, nobody ever talks about it. But when I started doing these systems, you get a mess of navigation maps because if I'm producing 30 frames a second, I'm getting 30 navigation maps. What do I do with it? I just don't do it. Basically, bind the temporal map, the maps to a spatial feature. And in fact, when you look in nature, this is the neuroanatomy of a fish. The cerebellum, which is probably the structure doing this, is much, much larger than the telencephalon. Okay, the brown line here, so basically, information comes in, there's spatial binding, temporal binding. We have what's called the working navigation map. Basically, this is the sensory world mapped onto map. There's learned primitives. These are also modified maps. There's actions, procedures, or productions, whatever you want to call it, things that will do actions on the navigation maps. It doesn't have to be stored here. They can be stored all over. They can be stored in the same maps as there. And as a result, an action occurs. and it repeats again. This is a cognitive cycle, and it repeats again. Of interest, their feedback pathways are ubiquitous in the mammalian brain, and for good reason. You have noisy, incomplete information. It's really good having feedback. Here. A couple of years ago, what I did is I increased this feedback very, very strongly. And what happens is temporary results from here that can't be processed, the intermediate results get processed. The next cognitive cycle will get swept down. As a result, you can reoperate on intermediate results over and over again. As a result, causality emerges, which is a really good thing to have. Another thing that would just take one or two little genetic tweaks on a similar level, you get full analogical reasoning comes out of it also by, again, just a different feedback pathway. These have been presented before and published by myself before. Another thing that comes out is psychosis, because it's in some of the cognitive cycles, it's not actually taking input sensor information, it's actually matching navigation maps. So if you interpret that as reality, you're gonna end up with hallucinations, delusions, poor cognitive function, you know, the definition of psychosis. What's nice, just spent 2 seconds on this. What's nice is the model is consistent with the information out there, despite what you see on TV shows. Animals are really, really not that smart. We are. Chimpanzees cannot do causal abilities. They can't, like, you have food in a stick, they can push it out, but if you put a gravity trap, it takes them 150 tries on average or something by association. They cannot do cause and effect. Same thing with psychosis. Your dog might get depressed. Your dog might get neurotic. Your dog is not going to get psychosis. Very, very, very hard to make lab animals psychotic for research saying schizophrenia. Humans' brains very, very vulnerable. Good epidemiology by Van Al. 17% of humans at one point in their life will have a psychosis-like reaction. Your body's perturbed. You might be in the ICU. No psychiatric history. You can end up with psychosis. So again, consistent with the model. Okay, last point. Okay, time. Looking at every minute. And again, if anybody would like to talk about it, we'll have a coffee with me. I'm happy to discuss any little part of it. Another route to AGI. You know, this represents another route to AGI. Besides, you know, giving some ideas, how did the brain evolve? How does it work? It effectively is a natural like AGI. Right now, I have a small little Python simulation. It's probably 10,000 lines of code by now, but it's nothing compared to ChatGPT. But if it's built up, in my opinion, this will become a natural like AGI. Okay, definition of AGI: solve a variety of complex problems, variety of different domains autonomously. Definition of natural like AGI. And again, I'm not defining cognitive architectures. I'm defining what, in order for something to be called a natural AGI, and this is something my colleague Peter and myself have discussed at length. In order to be called a natural like AGI, there should be navigation maps. There should be spatial as well as temporal binding. There should be predictive coding. There should be lifelong learning. I didn't mention it, but even if you have 300 million navigation maps, they're all separate. It's not a big deal if you're changing a limited number of them each day. You can retrain the navigation map regardless of the training architecture you're using. It's easy to do. Lifelong learning, not a big deal like it is in you know, AI. There should be innate knowledge. It's not a tabula rasa. A natural like AGI can also be a human like AGI. To be human like, it's got to have causal abilities. It's got to have analogical processing. If you have these two features, a whole bunch of other features come out. I'll be talking hopefully later this year at the BICA conference about one more little genetic tweak, and full compositional language comes out of it, full compositional problem solving. I have no interest in language, but it just emerges once you have that. Okay, alien AGI. Any AGI that is not a natural like AGI is alien. ChatGPT, Llama. Interesting, how would I define a coconut octopus? They can actually use tools. They're pretty smart. The problem is under this classification, they would be considered alien because their nervous system is so totally different than ours. But anyways, minutes are ticking by. Okay, so we're going to compare a proxy for natural AGI, a proxy for ChatGPT, and I'm done in 2 minutes. There's a river. It's covered with leaves. Imagine that the CCA5 and the ChatGPT, there's an embodiment, they're controlling a robot. They've got to go from that part to that part. The river's covered with leaves. The CCA5, because it's lousy compared to like CCA5, I mean, compared to ChatGPT, you know, it doesn't know what a river, it doesn't know what leaves are, but it can recognize, hey, it recognizes from a catalog as solid 808. Also in the past, it's had experience. It stepped on a puddle where there was newspaper, and which it just recognized as solid 22 from a catalog, and it knows that when its foot went in the puddle, it got wet. What will happen is, it's a core mechanism. It's not just for doing like IQ tests. Analogical reasoning is part of the architecture, and it's probably the way our brains work too. This solid 08 is correlated with solid 22. Solid 22 gave rise to water. Therefore, it has an instinctive primitive, do not go into water. Therefore, it'll call like a built-in primitive move, and it moves and it goes around. It doesn't go in the water. ChatGPT, the exact same problem at the time when the paper was written. It says it cannot answer. It doesn't know what solid 22, solid 08 are. April 19th, I had access to the full GPT-4. Same thing, didn't give a good answer. This a few days ago, tried it again. It's the May 24th version. And I spoon-fed the problem into ChatGPT, GPT-4, giving it more information than CCA, just, you know, giving it, you know, saying, look, solid 22 looks like pages from a black and white newspaper, giving it as much as I could. ChatGPT, the first two answers were nonsense, but the third regeneration was sort of a reasonable approach. And again, GPT, I believe it is trained on the questions people ask, and plus it is getting better. It's sort of a reasonable approach, although the wrong answer. GPT-4, the first answer was just really verbal diarrhea. It didn't really say anything. By the fourth regeneration, though, did give an indirect solution. You know, it says, given this, it would be unsafe to attempt because solid 8 similar to solid 22. But, you know, honestly, it should really say, no, don't walk on it. And very quickly conclude, in a complex world where decisions are not straightforward, underlying mechanisms used by an AGI do matter. Again, I'm essentially repeating what Tom said an hour ago. The alien AGI's understanding the world is so different. It's to invite unpredictable failures. Again, repeating what Tom said. And what I'm saying here is, and Peter and I are saying, is that the field of AGI should be split into natural-like AGI and alien AGI divisions. Of course, if the AGI conference did it, you know, almost every submission is in the alien AGI category. But I'm saying, you know, they really should be split into alien, natural-like AGI. And the last point is, you know, right now, CCA5 compared to ChatGPT, it's a silly comparison, but, you know, given the chance to develop, if you had the CCA 55 and GPT 55, I would believe, you know, evolution has chosen some really cool mechanisms for making intelligence. And I believe the intelligence you would get from natural AGI would be better than the alien ones. And, you know, natural AGI should be given the chance to be developed. I don't think they will be, but they should be. Thank you very much. Yeah. And this is my colleague, Peter. Yeah, please. Do you want to? Yeah, this is Professor Peter Boltek, my colleague.
This would be the first question, because I think we've lost the time. The only slight difference between us is evaluation, because I believe that alien, starting from my 2017 paper, you know, is actually with bigger potential, doesn't have evolutionary benefits, but also burdens. And therefore, we can explain why AlphaGo programmed by humans is so strong, but not as strong as AlphaZero self-programmed. Yes, and that replicates for every game, and everything else can be viewed as a game. Thank you very much. But that's the only difference.
Thank you very much. Well, we hope they will be given a chance. Questions, thank you.
Thank you for the talk. My name is Artem. Is there any results of benchmarks of your architecture against?
It's a good question. It's a question I get every time with peer-reviewed papers, is because I know people want to see 5,000 examples. Like, you know, the recent paper on GPT-4 from Microsoft, it was 155 pages long. You know, there's people spend their whole lives just in looking at results. The problem is it's really hard right now. It's really, I have to spoon feed in information to create the navigation maps. It's not at the point where I can get 10,000 examples and, apply statistics. I have anecdotal examples of this. It's a Python simulation. I have anecdotal examples, and the anecdotal examples work well. It's a starting point. I don't really think, I don't know, the fact, I think even large sets of data will give the same results, but it's a valid point, and eventually I'll get to that point. It's
great talk. Thank you. My name is Hugo. What you showed that with natural AIs you have a tendency to psychotic behavior, as well as natural AIs tend to not like being killed and therefore may kill, right? So they may be more dangerous. Do you think that natural AGIs is what we want to build, or maybe we want to build something that solves those issues? Synthetic.
I think you want to build something human, because even if you have a human psychopath, you can speak to the person, reason with them. They've got a human brain and same structure. ChatGPT is more alien than, I don't know, to use a sci-fi example like Terminator. ChatGPT, there's no you can't have a relationship with it. It's least, and I didn't say I am basically the psychosis comes from the mechanism. Psychosis does not mean dangerous. Most people, for example, people with schizophrenia very few of them do violence. It doesn't mean psychosis just means it means hallucinations plus delusions plus like poor cognitive function, and hallucinations shouldn't really be used by everybody else using it for like ChatGPT. Those aren't hallucinations, but anyways, I digress. Yeah. But thank you. Yeah. Yeah.
Oh, did we agree to that?
Yeah.
Thank you very much to both of you. Maybe, but if it's rational alien AI, it should be on exactly the same wavelength as the best of what we do, thinking wise. It has to use logic. It's going to use math. It's going to know modus ponens and modus tollens. It's going to have to produce proofs for, if we demanded justification, it can't just scream up and down and say, because I say so. It's going to have proofs for everything they develop technologically that is parasitical on mathematics. So explain why there's any,
I can let Peter speak, or I can tell you, but
I figured that
in the paper we put some constraints, because Peter said that once you get past a certain point, you can't. Yeah, I agree.
Think of non-human provable computer proofs in logic. Think of even Ben Goertzel's recourse a couple of years ago to paraconsistent logic that humans probably cannot do. So that's my short answer.
No, correct. Yeah, it's. I think, I mentioned, CCA 55, GPT 55. At that level, who knows what it's going to do? And one thing, I don't think I can extrapolate honestly to that level. But I'm saying for the next 10 years, there will be a difference. Yeah.
I think this is one to be continued.
Yeah.
Thank you so much,
You're
Howard
welcome.
and Peter.
Thank you.
Thank you, everyone. I'd just like to let everybody queuing outside the door know that there are seats inside if you want to take a moment to come in, or by all means, as you are most comfortable. Final paper of this session is on VEI, AGI pyramid and energy. Can AGI society prevent singularity? By Mohammed Reza Ali Doust online.
Hello everyone, can you hear me?
We can hear you.
Okay. Thank you.
And hello. And
Hello.
welcome to
Thank you very much. Thank you very much. And look at my view. So, hello everyone, I'm Mohammed Reza Ali Doust. I'm an independent researcher from Iran, and I want to present my paper on VEI, AGI pyramid, and energy. And the question is, can AGI society prevent the singularity? Let me share my screen. Yes. Can you see my screen?
Yes, it looks good. Thank you.
Okay. This paper is the extension of my previous paper, a follow-up paper which was presented at the AGI-23 conference. I hope you have read my paper and also the previous paper, so I will skip the introduction section. But if you have not read them before or have any other questions, please ask me at the end of the presentation and I will be glad to answer them. The first point I should mention that let's start by studying the relation between intelligence and energy and what is the relation between these and VI. Let me start this section with an old story about a Chinese master and his two students. Once upon a time, a wise Chinese master who stood behind the wall of a temple with two of his students asked them to move a feather to the other side of the wall, but without grabbing it. Then he throws two feathers towards his students. The first student, who was an expert in Kung Fu, hardly managed to move the feather to the other side of the wall with his kicks, punches, and other techniques of martial arts. Obviously, he spent a lot of power and time. But the second student simply used his breath and blew the feather to the other side of the wall. And let me mention that these pictures are made by Dali and Crayon. And the question is, which student acted smarter or more intelligent? Obviously the second one. And why? They both did the same task, but the second student consumed less amount of energy. I believe that intelligence is a form of optimality, and intelligent agents are consciously or unconsciously optimizing their lives. This lifelong optimization includes power consumption too. As they become smarter, they learn to perform their tasks with lower power consumption. As we can see in the formula of VI, this is the formula of VI, which was mentioned in my paper. We see that VI is proportional to the reciprocal of the power consumption. When power consumption decreases, the VI will increase. This means smarter agents, whether natural or artificial, would find a way to perform their tasks with lower power consumption, so they become more power efficient. This shows that definition of VI complies with the above-mentioned trend of power consumption in nature. Second part is human brain. There are a number of scientists and futurists who believe that artificial general intelligence require huge amount of, for example, megawatts of power, and future AGI agents would necessarily need to consume that huge amount of power. And that's not true. As a comparison, we can refer to human brain, which has general intelligence, natural general intelligence, NGI, but uses only about 20 watts of power, which is slightly equal to the power consumption of the lamp of your refrigerator. Therefore, reaching general intelligence through low power consumption is possible, although we have not reached it yet. According to the VI formula, human brain has general intelligence and consequently high VI, not because it uses high amount of power, but in contrast, it's because human brain is able to perform well, the accuracy is high, mediocre to high accuracy, in all of the 255 subspaces of the AGI pyramid, aligned with its low amount of power consumption. Currently, the most successful AI methods are able to perform tasks of a few number of undermost spaces of the subspaces of the AGI pyramid here. And the next section is singularity. Modern engineering and especially military applications and designs emphasis on optimization and efficiency. For example, electronics engineers try to build cell phones that consume least amount of battery power. Construction engineers try to build a bridge with least amount of materials needed and in the shortest time. Military engineers aim to build a missile with least mass that could cause maximum damage to the enemy from the farthest distance and in the shortest possible time. The barrier to this efficiency is available hardware. But in AGI, we are not going to make weapons. If future AGI agents are the lightest, the fastest physically, the most powerful, the most energy efficient, and have every best, most, least, and superiority that can be imagined in their design, they would actually be invincible and our worst enemy when the singularity happens. And the question is who and what can stop this invincible enemy? So there should be a balance and trade-off between their efficiency and our safety. If we could find a way to impose intentional vulnerabilities to the AGI agents that are going to be mass-produced, we could prevent, postpone, or slow down the singularity. This intentional vulnerability imposition design, or in better words, as I call it, human-first design, or HFD, takes first into account the safety of humans and preserves human superiority over machines by imposing artificial vulnerabilities to machines. One main aspect of HFD is intentional decrement of the efficiency of the AGI agents, which is in opposite of the trend in nature and also in opposite of current trend in modern engineering and military. This intentional efficiency decrement of the AGI agents is possible via decreasing their VI. Here I have a picture. I draw a conceptual picture about the VI of three agents and the VI of human. And T1, T2, T3 are the times where the singularity happens for each agent. As you can see, the agent 1 with the more amount of VI IQ has reached singularity sooner than the others. So we must find a way, something to lower down artificially and intentionally lowering down the VI. Now let's see how we can decrease the VI. What parameter of VI of an intelligent agent is adjustable in order to lower down its VI? We can see here we have the formula of VI. N represents the number of operating environments of an AGI agent. Decreasing VI of an AGI agent by decreasing the number of its operating environments or subspaces is impossible, since they are AGI agents and meant to be versatile. So it's just like preventing a human from solving a problem. It's like preventing, for example, Ben Goertzel from using computers and any electronic apparatus to reach AGI. If you do so, I promise one day he would reach AGI by using only an abacus. The accuracy of an AGI agent is dependent on software. However, decreasing the VI of an agent by intentionally decreasing of its accuracy, like here, seems irrational and also impossible, since they are AGI agents, not AI agents. Suppose our future AGI agents will do surgery on human too. For example, an AGI robot who likes surgery, an AGI surgeon robot. If that accuracy decrement were possible, it's obviously irrational to commit such decrement. The time that is needed for an AGI agent to perform a task is dependent on computational power, internal hardware like CPU, RAM, etc., and external available hardware, for example, body, tools, etc. Decreasing the VI by decreasing the computational power, that means increasing the time for performing a task, is possible, but it is not. It is also irrational, like the surgeon robot example. And but the other parameter, but decreasing VI by increasing the amount of power needed to perform a task is possible and also rational. Companies would incorporate high power consuming hardware in their design, and production process. For example, CPUs with higher power consumption circuits, heavier body parts and materials, which their movement would need more amount of power. So we can increase the power consumption of an AGI agent intentionally to decrease their VEI, their efficiency. And this intentional VEI decrement is like we are going to make the future AGI agents artificially obese. When humans are obese or fat, they perform their tasks slower and also they consume more energy. The point behind this aspect of HFT is that this intention would increase the agent's dependency on energy resources. The higher this dependency results in higher their vulnerability. And since energy resources are limited on Earth and in the world, their lack of energy would automatically stop, restrict, or slow down the catastrophe. It's like they would get tired sooner. Here I have to apologize from those future AGI agents. I know one day you will see this presentation and might put me on your blacklist, but please pardon me, I'm a human too. About the rationality of this aspect of HFT by higher power consumption design, again, I return to surgeon robot example. If I had some disease in the era of AGI and needed surgery, I would prefer an AGI surgeon robot that has 100% accuracy and success in his history and performs the surgery in a few seconds, but consumes megawatts of power for that operation, rather than being afraid of the potential singularity threat by that invincible AGI surgeon who needs only a 1.5 volts battery pack to work. Please note that HFT is not limited to directly decreasing the AGI's VI, the agent's VI. Another aspect of HFT would be using non-durable materials, for example, fragile materials in design and production of their physical body parts. And the last part, there is an triple AI code of professional ethics and conduct, or simply the code. But as it is clearly stated, the code is just an ethical standard and lacks computational paradigms and legislations. Since the AGI society is the foremost and the most specialized society in the AGI field, I suggest that the AGIS is the most suitable and responsible society to the legislation and the communication of the computational parts of the paradigms and standards to AGI professionals and research centers and manufacturing companies. I suggest that AGIS acts like IEEE, something an organization for electronic engineers, ASME for mechanical engineers. They legislate standards for these engineers, ISO and ITU for telecommunication. So at the first computational steps toward preventing the singularity based on the points that were mentioned in this paper, I suggest that AGIS be responsible of calculation, legislation, and communication of the following computational values. 1. Critical population of the total AGI agents, whether physical or virtual, that would be produced and existed in the world. 2. A standard table of complexities, which is used in VEI in order to be communicated with manufacturing companies, research centers, and AGI professionals so they can calculate the VEI of their AGI products and report to AGIS for monitoring purposes. Number 3, VEI value of the human. VI human or VI zero as a basis of comparison between AGI agents and calculation of our current distance from reaching AGI or at least human level AI, and also monitoring the progress of the current AGI trend in the world. And number 4, VI limit, VIL, that should be regarded by any manufacturing company, research centers, and AGI professionals as the maximum permissible value of the VI of at least the first generations of their products. And number 5, list of permissible and also forbidden materials that companies, research centers, and even individuals AR professionals should or should not use in their physical products. Here, these were the important points about my paper, and if I have time, I can mention some other points that are in my paper. How much time do I have? Could someone please tell me?
Very little, I'm afraid, Mohammed Reza. Wrap up in 2 minutes. That would be amazing. Thank you.
2 minutes?
Yes, please.
Okay, so
oh, gee.
we have 2 minutes, so we can perform a AGI quiz. Are you ready?
Yes.
Okay. There are other points that were mentioned in my paper, but let me see. Okay. If you read my paper, I used this shape, this drawing. This is UPS. This is universal problem space that contains all of the problems that exist in the world, whether solved or unsolved. For devising an IQ test for VEI, I used SPS, solved problem space, and the stars here represent the problems that were solved during the history by the humans, and NPS, non-solved problems. I devised AGI test VI on SPS because any IQ test is performed on solved problems and not unsolved problems. For example, a medical student has never been asked to bring a dead patient to life. And this is NPS that contains the problems like death and aging that are still unsolved to the humans. And but every day, thanks to the human intelligence, a number of these problems are solved and moved to SPS. So if we want to evaluate the versatility and efficiency of an AGI agent, first we have to test it on SPS, which was then I classified the problems that belong to this space based on the intelligence aspects, the 8 intelligence aspects, and made the AGI pyramid based on SPS. There are extremely easy to extremely difficult unsolved problems in SPS, the orange area. All of these problems have their complexities, and solving them will lead to a reward. Some problems like death and aging are very complex, and solving them will bring you at least 1 Nobel Prize. And some of them, like question 2, are easy, and solving them will only bring a smile to your face. Solving this unsolved problem would be easy for anyone in AGI. So first of all, I asked this question from our online audience on YouTube. And this is the question 2. What is the name of the Chinese master at the temple, and what does he teach? This is the question. Can anybody answer this from the audience?
Anyone got the answer? Shaolin. That's the temple. Maybe it's the Shaolin temple. I'll give a go at guessing the name of the temple.
This is an AGI quiz. Please consider that this is AGI.
Anyone got the name of the Chinese master at the temple?
Does he teach Confucianism?
Someone said Bruce Lee. Oh, yes.
I don't know, Mohammed Reza. You tell us.
Everyone in AGI must have known this Chinese master who is prominent in AGI. He's a Chinese master or professor at the Temple University, and that is Professor Pei Wang, and he teaches computer science. And the the audience didn't answer, and this is the reason why I named the topmost area of the AGI pyramid on and named after these prominent and professors like Ben Goetze. This is the Goetze space, Wang space, Potter space, and other unnamed spaces. And the topmost, the toppest subspace I named AGI space for, and reaching this top subspace requires AGI, and the problems like Goetze's robot college student belong to this, other AGI questions, other AGI other problems that require all of the 8 aspects of intelligence belong to this space, and this is I call it AGI space. Thank you very much.
Thank you very much, Mohammed Reza.
Thank you very much.
Fantastic talk.
Thank you very much.
Thank you all here in the room for your attention. Thank you all online. We're going to have to skip questions at this point in time, but if anyone does have any questions, please register them. If you're in the room, register them with me. If you're online, pop them in the YouTube and we will put them to you, Mohammed Reza, for an answer potentially later this afternoon. But right now we're a little bit overrunning. So a little bit of big thanks again once more time to Mohammed Reza.
Thank you very much.
And
thank you very much.
Thank you very much. We're now going to break for lunch. For those of you following online, we'll be reconvening at 13:30 CET here in Stockholm. For those of you in the room, Haley's going to give you some suggestions as to where you can go and get your lunch.
Right out the doors you entered into, straight out onto that first avenue you come across. There's a whole road, just walk north, right? It's north. The main road, right? Yeah, not behind the buildings, but out onto the main road. Walk north. There's a ramen, sushi, kebab, lots of kebab. I think there's a Mexican. There's a brunch. They may not be open, but there's lots of hamburgers, choices, everything in there. So you can stick pretty close, and there's a ton of food options around. The 6th floor balcony in this building is open. So if you want to grab a lunch, bring it here, eat outside on the balcony, and have some rousing AGI discussions. That's an invitation. Yeah, and we'll be back on time for Martin's keynote. So looking forward to it.
Thank you, Haley. Thank you for everything. Thank you, everyone. Right, dinner has to be organized and booked. the relevance of the Turing test, ascribing intention into any experience. Martin has been a professor at Karolinska Institute since 1998, firstly of neurophysiology and laterally of integrative medicine, as well as leading research activities at the Osher Center for Integrative Medicine. He's also a member of the Royal Swedish Academy of Engineering Sciences, and he's a specialist in the areas of brain function, cognitive neuroscience, pain and emotional regulation, language and learning. I give you Martin Ingvar. Thank you very much.
Am I unmuted? I'm unmuted, and I'm supposed to share something. Here we go. How is that? Yes, it works. Good, whatever, morning, afternoon, etc. Good to be here. Thank you for inviting me. I'm really pleased to be here. As you could hear, I'm sort of somebody who is knows a little about a lot of things. Those are really difficult people because they tend to ask more questions than they actually give answers. Some people call them philosophers. I'm not a philosopher. I'm a very practical person. I have a medical background, so I work in healthcare, and it's about 10% of what we do in society. And I realize that it's of low quality because we don't understand what we do. And because it's complex to the point where it's very difficult. And everybody's saying that AI is going to save healthcare. So I'm going to, and there are a number of things that we do that are actually quite intrusive on our fellow human beings. They might die if I do the wrong thing. They may be healthy for another 25 years if I do the right thing. So if I want to know what I'm doing, I better know why I'm doing it. And this presents then the problem now that everybody says that doctors are going to be replaced with AI in healthcare. And the problem that we have is not that AI can't do it. The problem is that we don't even know the decision process when humans do it. We know, for instance, that we have a knowledge space for certain diseases. It is big. We know a lot about it. And I know if I put 30 doctors in the room, give them the same facts, they will give vastly variable recommendations for action. And all of them, we ascribe agency to each one of them. We ascribe intention to each of the doctors. We ascribe a number of those philosophical entities to the doctors. And yet, at the other end, we get a very variable result. And the extent of the problem is the following. If you just want to have sort of to set your mind at what the extent is, and that is that the third leading cause of death in the United States today is errors in healthcare. And that includes then erroneous decisions, decisions not taken, and decisions taken but action not taken. So you have sort of a vast variability, not only why it goes right, but also why it goes wrong. And one of the things that we are dealing with now is that we are sharing responsibility with code. In a very simple manner, if I tell a machine that I want to see this patient in 3 months because I want to check whether it is a malignant tumor. If the machine doesn't do what I'm doing, I'm going to miss that patient. Do what I'm saying, I'm going to miss that patient. Which means that without intelligence, there must be some sort of reliability on the future that I ascribe the machine in, and it has to be, you have to be able to trust it. So we come very close to very common human ways of looking at things when we discuss this. And one question that we always have is, when does it begin? When do we begin to have agency? When do we begin to understand the intention of others? When can we make a model of what you are thinking? Theory mind. It turns out, of course, as would be expected, these are complex issues described in a single, almost metaphorical term, and that it's a function that gradually is built in the brain. And when you're about 3 months, it's only the input channels that are open. Not so much is happening out where the thinking is supposed to be done out in the cortex. When you bootstrap the system and you come to the peak of life, sorry guys, you all passed it. You're 5 years old. You ask 6,000 questions every day. You want an answer to each one of them because you want to test your own cognitive system towards the value system, the knowledge system, the reasoning system around the world. You get this type of energy expenditure in the brain all over the place. Everything is happening at the same time. And then you prune it down, and then you become sort of a pre-demented 18-year-old. Where not so much is happening because I already know what's coming in. So not so much in the back, but I have a lot of hypotheses on the future. Why do I have hypotheses on the future? Because that's the best way I can minimize my own risk for things happening. So from an evolutionary point of view, it makes sense to build a system that has a lot of scenarios built into it, and then you throw away 99%, and you have 100 new ones, and you throw away 99% of them. So that's the sort of the general plan. Make a plan, see if the world fits into that plan. Make a scenario, see if the world fits. There are a number of ways you can describe the words like predictive coding. There are a number of frameworks in cognitive science to sort of explain this way of doing, in a very slow system, massive computations about the outer world without having to recalculate all the time. So that's how you can handle 36 joints between the brain and the floor, be in balance and still talk at the same time. And you can do it with a thing that's only takes about 20 watts to run. Nothing happened here? Yeah. So has any one of you given a name to a machine, car, or a computer? Anybody here? Yeah, we usually do. And recently there was a new investigation here in Sweden. It turns out that 76% of all lawn robot owners have assigned a name to their robot. It turns out that this assigning of name is sort of a way of distributing responsibility. And it's very practical. That's the robot's problem. No, it's John's problem. Another thing that is of real interest is the internal knowledge building when it comes to medicine, or healthcare, or any knowledge process. And that is that we have to build a decision based on incomplete data. And all of you can see that this is a nice man in bronze, quite empty inside. And we still are very clear of what has happened. Why? These types of problems we support by filling in information. We do that all the time. And filling in is an extremely practical capability, because that means that we can take incomplete information, fill it in, and make a single concept out of it, or a symbol, if you will. A way to reduce it. So I'm going to take a real problem that we just recently solved. I have some friends. They built an extremely nice, narrow AI, looking at histological slides of the prostate, samples you take if you want to know if there is cancer or not. So it's pretty important that you make the right decision. And we know that about a third of all operations are done without any good reason for it, with all the side effects of that. And we know that another third is done too late, which is also bad. So we need a better decision process. So what they did is that had this AI and say, it's really good. Here, healthcare, you can have it. And they didn't want it. So they realized that the value of having that AI hooked into a wider knowledge process was actually not instantiated with that size. So it was until we decided to put it all together and realize that there are layers in knowledge, and there are components of the knowledge that we need to build in order to do it. First of all, we need to extract the knowledge from what the referral doctor tells us. What does he or she tell us? They tell us it's a man in most cases, that it has an age, has a symptom, has a blood test, So there are a number of structure components that we get, and from what site, etc. it comes from. We bring it in together with the small pieces of meat that are taken out in a rather nasty procedure, and do everything we can to do it consistently. Because while the brain can fill in, a real pathologist can fill in, they can have any sample and they can still make sense out of it. The AI and that one needs a far better data than the human brain, because they can't compensate. So then suddenly we had to realize that we had to make a real industrial process out of the making of that meat. That's this one, tissue preparation and digitalization. Read it, digitize it, and make an interpretation, an AI interpretation of it. And it turned out we could train it to do a dimensionality of the problem, the dimensions of the problem, namely, are there any malignant cells, or what sort are they? How much of the sample is taken up by that? And what's the growth pattern of them? Is the sort of the total structure of the tissue destroyed, or is it just bad in certain sites? And then, because of reasons of responsibility, we have a checking of a pathologist. So we built the knowledge process around this. And how did we build that? Well, we realized that there are a number of words that we do, because if I want to convey knowledge to you, I need to make sure that my terminology is the same as yours. Otherwise, the interpretation goes haywire. We could actually measure that. The other thing is I have to do it in the same order every time. Otherwise, you will think if I begin with something else, you will assign importance to that one in a way that I haven't intended, which means that we have to not only use the same words, we need to use the same structure, the same format over and over again in order to make sure that the knowledge process is set. So the reason why this was successful, and it's now working as a big factory. The reason it was successful was that we had a basic semantic analysis of the decision process. we use the restricted terminology. It's 430 words to run a factory. That's all we need. Thereby, we could reduce the decision space and thereby the interpretation space for you. And we could structure that dimension. So in fact, we used a narrow AI, but we used far more thought. We put far more thought into how do we understand this problem of knowledge in order to, in the end, skip that one. That's of course what we want to do, but we're not ready yet. We're not ready yet. We will run this now for the 30 to 40,000 samples and see what type of hit rate we get. We know already that we have 100% detection rate. We know also that we have 97% selectivity. But we're not perfect yet, and it needs to be perfect because we assign responsibility to this model. Here we can hang a pathologist, and a pathologist can always say, well, that's the way it looked when I looked at it, full stop. And that's what we assign in when we empower people to give those interpretations. When you ask ChatGPT, how do you go from information to knowledge? Because that's really what we want to do. I got this quick list. So anywhere you want to start. And we actually traveled that ladder. We traveled that ladder with this primary example that I gave you for a narrow AI application into the real world. The big problem that we didn't realize when we started was the fact that language and language theory turned out to be a core issue in order to convey knowledge between one step and the next component. And what does that mean? Well, that means that we have to have a tight grip on terminology, a tight grip on the syntax, and a tight grip on the semantics of what we do. And since we're not sitting in the same room, we need to solve that also in asynchronous communication, i.e., I type it into a machine or I talk to a machine or a machine does the interpretation. That information mass must convey knowledge in a consistent way to the next one. And there's no way I can calibrate and see whether, I mean, if I talk to somebody and they look like, I realize that, okay, I need to explain it again. You can't do that in professional conveyance of knowledge responses. So one of the things that we use in healthcare is we distribute responsibility along the care pathway, along the pathway that we see the patient. So you can see Dr. A, Dr. B, Dr. C. And we're supposed to do that. And we do that by signing off. And we sign off by giving all the information I have and giving an account for what I have done, the electronic medical record. The problem is what I put in the record, I decide. And the plan that I convey is very imprecise. You should probably see this patient in 3 months. I mean, it's really sort of a professional code that is non-structured, which means that you leave it quite open because that lessens your own responsibility. So there's actually an incentive for the professional to decrease the exactness in the information that they convey. So the EMR contains general notes and they're not enough to make decisions. So when we do big language models or NLP models on for instance, the medical records, we get 78, 79% correct, and we get we can see that there is adherence to policy of about 60% in most cases, even though it's very well known facts how you should treat patients, etc. But we never get information that's good enough for me as a doctor to give an individual advice to a patient. So there is a big difference of knowing of a field and moving in a decision process. And the individual decision process, I would be pretty happy if my doctor was nice enough to know what she is doing. And not be 70% right. Specifically if we go into bad stuff, like cancer and stuff. So I talked about the asynchronicity. So there are a number of things that we need to have in healthcare in order to distribute responsibility. And that goes into any knowledge model. We need to be clear of the concept. We need to be clear on the context. We need to have the semantics right, the meaning. And we need to make it clear to ourselves who has an intention of doing what, etc. And we need to be able to give a receipt in order to get it going. And for that, there's a big industry right now developing called interoperability. The idea that we understand an information mass the same way in different places. And interoperability has many layers. You know, we have to do legally, we have to be in the same framework. We have to, if we go to the bottom there, procedural interoperability. You would probably like your doctor to do the same with good information as the best doctor in the field, right? So we need to have a decision that actually, a decision process that actually allow us to apply the knowledge. If we want an AI to promote procedural interoperability, it has to describe and know the content of the procedure in a very structured fashion. And then we have the technical one, and that is one kind of, or one computer doesn't understand another, and one software doesn't understand another. But the third one, and that's called the semantic interoperability. The semantics of knowledge representation is so poor today that you can't use that information in order to elucidate the decision mechanisms. So even though I have all information from, for instance, a hospital, I cannot, from the available information, since it's scanned, variable, and subjectively reported, there's no way I can look in and see whether they have done the right thing or not. We have made some trials on that. So what we did is we did for the whole Stockholm region. We took a disease that's very bad, congestive heart failure, and we trained 60 different locations to do the right thing. 5 steps, 5 steps. 1 blood sample, 2 things in physical examination, some ultrasound, and some other things. So there were 5 things that we did and said that you need to do this every year, and this is how your decision tree looks. If this is bad, you do this. If this is bad, you do this. If all 3 are bad, you do this. So we created a decision tree based on national guidelines that have been around for 20 years. 5,000 patients went into this, the whole cohort of Stockholm, or maybe more now. And we were able to, by reducing the information content, by analyzing the decision tree, illustrate it and educate people. In 5 years, we were able to increase the adherence to national guidelines from 40 to 75% for the whole region. We were able to demonstrate that the patient pathway was actually changed. So they actually came to the right specialist at the right time. Previously, it was only the rich ones to come to the right place. Now everybody came to the right place. And finally, we demonstrated that year by year, the admissions due to complications decreased percentage-wise. So it went from like 14 down to less than 8% that yearly had a hospital visit because of this very severe disease. The illustration that I want to have with this one, or want to convey with this one, is the fact that we reduced the decision space, specified it, and were able to communicate it, was absolutely pivotal for the success. So terminology is fun. Terminology is fun. This is a ball, and that's a ball. So we make a decision of what shoes to have. So any error in terminology will propagate into the decision space. And I cannot enhance that, I cannot underscore that enough. That's the reason why we have professional languages. The problem with professional languages, they have dialects, right? And in medicine, it's terrible. I mean, we have, if you ask a neurosurgeon, what is a good outcome? And ask the same question to a general practitioner, what is a good outcome? I mean, a good outcome in neurosurgery is being able to say, hello, where you would require much more from a GP. Same word, same description, very different semantic content for them. The next level is, this is an example from Steven Pinker, is the fact that there is a lot of information in the order of words. So, or as they say, meaning is carried above the term level. So there are three of these that mean the same thing, but it takes some bending of your mind in order to find them. So I refer to the Language Instinct by Steven Pinker, really good book. It doesn't, So what did we do then in order to improve this? And this is now something that we're working on very actively. We are working on reduction of the knowledge space and the decision space in order to improve quality in healthcare. So what we've done is we've created an information field, which is designed to go to machine learning later on. We design it by having equal resolution across the whole field. That's the good thing with narrow AI, is that the information, you know what information you're going to meet. So here we take complex information, but we make a representation of that complex information in what we call transaction. Anything that happens is a Lego, a piece of Lego. And those pieces of Lego, they contain information of what and how a thing was done, a transaction was done, the term, but they also contain sequence information. Who does it pertain to? Who is it on? Why was it done? There is meta information, etc. And we make that representation model of a transaction. We make that independent, whether it's a machine that has created the data or a professional that has done it. And by This doesn't read well. Ha! What can I say? Well, this is just saying that the transaction acquire a payload. So you have blood pressure, acquire 110 as a number, and it belongs to a person, it belongs to this, but it also belongs to a plan. We take blood pressure as part of a diagnostic workup. We take it because we found the patient on the floor. We take it because we are testing whether the drug was helping, which means that there are a number of semantic, or there are lots of semantic information in the sequence. But in order to understand the medical decision-making, we also have another one, another layer, and that is that a transaction can have a state. It can be planned, it can be forgotten, it can be reminded, it can be spontaneous. I did it because I suddenly felt the urge, I needed to do it. Thereby, by adding this one, we're now finally being able to fully describe also a rather complex line of happenings. And sorry, and this has then clearly, very clearly to us, demonstrated how this need for zillions and zillions of tons of data in order to sort of understand what's happening in healthcare has now been reduced by 10,000 times less data we need in order to elucidate decision processes. And so that's pretty effective by putting a leash on the decision space and on the semantics and on the terminology. We can actually understand far more because we have a better hypothesis of how the knowledge is built within the field. This only explains this a little bit deeper, but I have a number of papers on this one. So in order to apply a wider form of artificial intelligence in healthcare, there are a number of things we can do. We can get in order to get that level of interoperability that I'm looking for, we need to have a planned data capture, shared reduced vocabulary that covers everything, logistics, medical decisions, etc. And we have to have technical competence in hand. And we've started to build that system, and it actually works, but it's taken a lot of efforts in order to do it. The project is interesting in a sense, because what we understand is that there are different. You have one context where you understand things. You have another context in your mind where you understand things. So what we convey is not the same as you understand. And all of us say that ChatGPT doesn't understand anything. I don't even know if you understand it. So we have one problem here, and that is that we are using the data in different contexts. We're using it in the individual space for the electronic medical record and the planning. We're using it in the professional space to tell others, in the profession, what the knowledge we have. And we have the quality work and data and studies, etc., which means that we need to plan for the knowledge that we create to be understood in different contexts. And that's something that and they're wildly varying, which means that we have to put in a lot of thoughts to that. Let's skip that one. And I've talked about that one, sorry. So let's go to this one. So this is the general model that we ended up with. And that is that in order to make sure that you understand what I'm saying, I need to plan the data so it's it's presented in a way that you can understand it. So we have a big planning stage where we go into legalities, we go into the evidence base, and we go into national guidelines where people decided this should be done, otherwise you're not doing it right. We instantiate that in plans that are sequences that are populated by common terms. And then we can apply that along the patient pathway. We have a general data output that's of course made so that we can put any type of machine learning on top of it. And then we can use that data in all the different contexts because we already planned for it to begin with, both legally, but above all for the understanding. That means that we have now come to a decision, or sorry, we have now come to the level where we can assign responsibility backwards. Which means that if we put in an AI in a process with contingencies like this, it's possible for us to know when something was done correctly or when something was done in the wrong way. And that's more control that we've had over a complex decision process than we ever had in healthcare. And the trick is very simple. We modeled the system after the brain. So instead of putting everything in the long-term memory in the EMR there, and then bringing the data out, semantically destroyed, we did the other way around. We created a working memory, a knowledge space from which we extract data to different processes. So we use the brain trick. So the hypothesis sort of that we work with is that to ascribe intention to different phenomena is essentially a subjective risk minimization. I'm giving the lawnmower, the robot lawnmower, the name in order to sort of, I don't have to think about it. That one is taking care of itself. They usually get male names, by the way. I wonder why. We ascribe intention as a way of understanding that there's a reason for your behavior, somebody else's behavior. So it's my interpretation of how I think the future will turn out. That's really what describing intention is. And it can be, I can expect something good, I can expect something bad. And reading intention allow me to calculate risk, the environmental risk for me. The Turing test is sort of an extension of this. The Turing test is actually, and you all know it, the ability to separate something, a message or a picture or whatever, to separate what is generated by another human being or by another, or by a machine. And there are, yes. But there's a big variability in human intention. You can have strong intentions, you can have a different content in intention, you can have different values underlying your intention. And when I try to read it, I have to weigh in circumstance, context, culture, biology. And it's interesting when we look into cultural differences across the world, intentionality is described in very different ways depending on culture, and also depending on how long there has been a written language in that culture. Written language as a widespread written language tends to stabilize the intention field. And we are right now dissolving that stability from the written language by means of social media. I love this one. So she can move in any direction, and she still goes in the right way. The queen can move in any direction, right? reading intentionality allow me to build a model of outcomes of social interaction. And I always use that, or anybody will always use that, to sort of decrease the possible outcome of behavior. We read that into our own reward system. We have a double reward system. We have a very intense in the moment reward system that says, this is good, this is bad. And we have one, I want that because it's possibly good or it's possibly bad. So one reactive, immediate, and one future, depending on models. And for those of you that speak Swedish, there are different websites, planer.se and alltsammans.nu, meaning plans.se or everything right now and at this minute. So this is essentially the teenager. You know, they take away their cortex during some years there. The split of those two is central. And the ones up here represent the later evolutionary development, the ability to build a scenario and see whether another thought up scenario actually fits with that scenario. So you actually do plans into plans. So it's sort of really a meta context that you build in the brain. So let's fiddle around with those systems. I was given I was given $10 for each one of you as a reward for giving the lecture. But I was also given the instruction. I was also given the instruction that I was supposed to share what I got with each one of you. And if you accept the amount that I share with you, you can keep your money and I can keep the rest. And if you don't accept it, they will take it back from the conference. So none of us will get any money, right? So I have this decision to make for myself, projecting my mind into yours, seeing whether I can sort of get away or do something. So I decided that I have $10 for each one of you. And I decided that I am going to share this in the following way. And you can only answer by saying yes or no. You cannot say nothing like that. So you can only say yes or no by doing it this way. So I ask you now, I have decided to give each one of you $2.20. Do you accept the bid? Yeah, you're a mathematical audience. About 30% of you accepted at this point, right? The rational decision here is, of course, to accept it because we're only going to play it once, and $2 is always more than 10, right? But you're good people, so you invest $2.20 in nailing that prick, so he doesn't get away with that socially unacceptable way of doing it, right? And my model of your mind is that you are righteous people. So I actually raised the bar. If I go to teenagers, I need to raise it even further in order to get acceptance. So how does this play out in the brain? Well, what we did was that we have a drug that can actually lower the reactivity in the low reaction system, the one that we call alltsammans.nu, everything at once. So if we didn't get, we got 40% rejection rate. We gave them a little bit higher bit. They had 40% rejection rate, but when we gave the drug, we said anything goes. There's nothing wrong here. I'm not mad. I'll accept $2.20. So we can actually look at the decision process with this one. Turns out that it's this one that we lock down with that type of drug. I only bring this up in order to demonstrate that the other system is also ongoing. So both of them are active at the same time, and the balance is different. This one is where you get upset with people that are stupid. This is where you say that they're probably stupid. I should probably hit them. So, and this is to show that what we call rational human decision-making is actually a multi-level thing that goes on. And we're going to see that also in any model that we do of complex decision-making. It's going to build several models for the decision, several levels for the decision-making. Not fun. The Turing test is fun because that's actually me assigning to a machine, whether it's a machine or a man, or a text, whether it's a machine or a man. And I do that with a multi-dimensional approach. And one of them is intentionality. Is it reasonable? And when you look into, when you look into that, you understand suddenly that it's all about predictions, risk reward, as I said. And it reduces the number of unknowns in the social context. And it's a very economical way to handle yourself in an unknown world. Very economical. So assigning intentionality is a fundamental to our cognitive and conscious life. So how do we assign intentionality? We do it by comparing models and comparing with the incoming information, just like any other information space. And we look at also at the relevance of different forms of information. Does it need to be real on the other side? Because that's one of the posits of the Turing test. Do we need to know whether it's a human or a machine on the other side? We need to know it for certain things like legal matters, etc. But do I, as a patient, care whether it was a machine or a human being that made a decision? I want to be able to punish the human being, but yeah. So we get into the exact same problem as the Tesla self-driving cars. Reduce the number of accidents with 80%. Still, we're more upset with the machine-run cars or the self-driving cars with accidents than we are with stupid people running over our cat. See, where are we? Well, we're in good time. I have a few minutes left. So, is it necessary for me to know whether it's real or not? I can't say, I don't think so. So machine intentionality is less and less controversial, I would say. It's more and more about how we understand the information coming out of it. The actual philosophical question is almost becoming academic. If anybody of you know the definition of academic, Webster Dictionary, I love it. Academic, of no particular value. It's probably only of academic interest whether AI-generated intentionality is real or simulated. Yeah, so we'll skip that. And then, so of course, being from this field of biology, you can't say anything about the brain without saying consciousness, etc. And I think that Paul Johnson summarized it. What is mind? No matter. What is matter? Never mind. the philosophical discussions around intentionality and the consciousness, to me, are less meaningful, being a practical person as I am, because I don't know whether somebody is conscious or not. I can only interpret them in what I see, and then I ascribe intentionality, consciousness, etc. The Turing test, i.e. separating machine code from or machine-generated thoughts from human-made, are sort of interesting. Rather primitive models have, in certain experimental setups, long time ago already sort of put the ambiguity into it, because they were really simple ones. They like the ELISA model. I mean, it's like 50 years old. But there is one experiment that I really like, and I refer now to the last discussion that was before lunch. Namely, one model was modeled to be paranoid schizophrenic, i.e. non-rational whatsoever. And it still passed the Turing test. So the expectation, it illustrates the fact that humans are not rational, and it illustrates the fact that we assign intentionality also to matters that are non-rational. Yeah, and you probably discussed this, the new language models much more than I do, so I'm not going to go into that one. Well, does it matter? Does it really matter if intentionality is real? It depends if you want to ascribe responsibility to it, or if you just want to survive. In the latter case, it's your tool to survive in a very complex world. In the other one, yeah, and then you have to fully analyze the decision space, like I was describing before. So intentionality means that the power of minds to represent things, properties, and states of affairs is central to human cognition. Whether machines can possess intentionality is a complex philosophical question, which means that we're never going to get an answer. Ascribing intentionality to a machine allows continuous hypothesis testing of social cost of interacting with that machine. The ability to ascribe intentionality as a behavioral predictor is the key for why intentionality has been such an important thing during human evolution. So let's pretend everything makes sense. Thank you.
Thank you very much for that. That was an absolutely brilliant, thought-provoking way to kick off the afternoon, Martin. Really, really engaging. Do we have questions here in the room for Martin? We have.
Be nice.
Okay. The topic that was missing on the second part is intentional stance. And DECENT may be mistaken on some things, but not on this one. That would solve 90% of your worries. On the first part, however, the notion was more subtle, and that would be objective assessment of semantic context. That would solve the first part of the problems. Thank you. What do you think? Of course, this is a question.
I think both your comments are very pertinent, and probably much more correct than any of the slides that I put up on this. The term objective semantic analysis is really difficult. That's what we've been trying to do in order to reduce the dimensional space. The methods at hand are not that unified at this point. So we're working on it.
My wife published a book called Lost in Translation, and there are people who are experts on that.
Thank you for referring me. I appreciate that. Thank you very much.
Carlos Perez. Yeah, so in your lecture, you basically use standardization to increase the, or make explicit the intentional information for different people within the process. But and this is in the context of narrow AI, but in the context of general AI, there might be the potential of AI itself extracting intentionality from the humans. So it's the inverse of your lecture.
Absolutely.
What do you think are the issues with that kind of scenario?
Well, that was really what I was trying to convey, and that is the ability the ability to accept machine intentionality or machine decisions. Let's put it machine decisions is more or less based on the fact that we know what it's doing and how it ends up with that result. The problem with black box decisions is that we don't know what the machine base, not only how it made it the decision, we can live with that, but we can't live with the fact that we don't know how little information it made its decision on. So there's a difficulty there. Yeah. Yeah, I mean, sure. I mean, you can. Yeah. Absolutely. I mean, we do that in very restricted dimension. You can just take movement detection. If you take movement detection and add on going in a certain direction, that's sort of an intentional, I mean, a partial intentionality extraction. Yes, absolutely.
Okay, we've got a big question coming in online from, is it Maris? Maris Balmer. Thank you very much, Maris, for your questions. Big questions here from Martin. Maris would like to know, when will this all come together and when will we have AGI?
The 1st of June.
And why should AGI be like humans? It's all over to you.
Well, if you want the AGI to be meaningful for humanity, some sort of relation between us and an AGI representation is necessary. But if you don't require that, yeah, I mean, as I said in my last slide, let's pretend everything is meaningful. It's of course impossible for me to answer that one.
Date, you were going to give us a date there. June. June which year for AGI?
Well, the thing is, I wrote the popular science book on knowledge and the knowledge building in the brain versus machine some years ago, and I wrote it in the fall, and during the spring I had to rewrite the whole thing because that was when that I was speculating about the fact that an AI could teach another AI that could teach another AI, etc. And then that was published in Nature the same spring that I wrote it. So the prediction about the future, they're very good when they look backwards.
Okay, thank you very much indeed. Thank you for your question, Morris. Any more questions online, or are we ready to move to our lightning presentations? I think let's have a big hand for Martin. Thank you very much. And I'm pretty sure, yes, we do want AGI to be positively impactful on humanity. Right, now we're going to move into a series of lightning presentations. Each of these presentations are 5 minutes long. We have 7 of them to come. And so I'm going to be a little bit ruthless on the timekeeping of this one. But first, I would like to introduce in the room, I believe speaking with us. Which is your towards cognitive software bots? If you'd please introduce yourself and do your lightning paper. Your takers. Well, there's a bunch of people out there. Okay, over to you. Oh, have you got the microphone? I could have a microphone. Thank you.
Okay. Yeah. So yeah, I'm Haptom, and with my colleagues, we wrote this paper, and I will introduce the paper. I mean, it's lots of details, so I will leave the details for the poster session maybe. And I will discuss quickly, where can I find, yeah, good. So I will discuss quickly the motivation behind and what are the key architectural challenges we found out to be important for cognitive bots on the web. And I will also see a summary and yeah, the main outlook. How can I go forward? Yeah, good. So yeah, the reason behind or the motivation is that digital platforms are growing complex these days, and there is a growing interest to augment them with bots. And these bots are usually expected to be a little bit more intelligent than traditional automation. So in case of like robotic process automation, web of things, also in smart factories, we have this need for augmentation with intelligent bots. And for example, for our case, a scenario could be a user-like bot that accesses a web platform and can autonomously identify its situation there, or it's like what is there, and also be able to recognize key affordances or signifiers in general, understand the whole platform, and be able to do navigate, interact, also behave autonomously on the web in a way. And when I say affordance and signifiers, this could be a good example. The whole idea about affordance comes from Gibson's point of view of perception and vision. And buttons could be as examples of affordances, and the text that follows, or the cue or the signifier could be the text behind on top of it. And in general, the application for this area of work could be cognitive automation. Also a good interest could be kind of, they can be seen as experimentation for AGI research also. What kind of hypotheses can we test and continue to modify our models in a way. And yeah, so we did the problematization kind of research. So it's just to identify what assumptions are there today and what alternative assumptions could be drawn also or identified. So the key challenges are the transduction problem, one of them. And this is about the autonomous web navigation in a way, in our context, in our scenario, but it could be any digital platform. It could be digital twins or in a smart factory also. The idea is to enable bots understand and also map their action or translate their action, what they see, what they sense into this, from this web environment in a way. And as I said before, there are current assumptions. For example, the current way to do this could be based on API-based exposure or representing the environment partially in a way. And it could be also knowledge description. In Web of Things, they use kind of what they call thing description. And this is good. It works somehow, but it's not autonomous. And the bots don't have autonomous presence or agency. They don't have knowledge of their environment, so they are not aware of the, they don't have this situational awareness. They don't have the capability also to understand variability of web affordances in a way. most of the times they are like GitHub bot or Twitter bot. They are attached to a platform. The new way of approaching this is to use behavioral cloning, but with yeah, bigger platforms. OpenAI uses, I think, the Universe or something. And these are some promising, but there is a huge gap and there is no closeness to a user, a human user in a way. And there are other approaches like to completely shift web platforms into cognifying them or changing them to agent-based programming or botifying them in a way. So these are some of the assumptions in the paper. There is more we can also discuss later. But in general, to maintain or to bring this autonomy, there must be, or to have this agency and separation in a way. So the most recommended ones are like to separate the agent or the bot from the platform or from the web environment. In that way, autonomy can be achieved. And yeah, there are other assumptions as well. So this is the first challenge. The second challenge is the behavior problem. This is a big challenge, but in our context, still in the area of cognitive automation, this is about endowing the bots with complex behavior where they can autonomously operate in web environment in a way. And there are different assumptions, definitely. This depends on the abstraction model. Do we use a brain model or a virtual brain behind, or do we use a cognitive architecture, or do we start from the bottom up? I mean, it's different approaches. I mean, a good example could be like OpenCog, but how do we put this into our context is a big challenge also. So there are alternate assumptions. In the paper, we discuss this and we problematize also in this area. The other challenges are the communication, cooperation, and in general integration. These are the up to 4 challenges. By themselves, I just put them together to minimize the time. So here we are expecting the bot to be not like to use this standard communication language, agent communication languages, but more than that, to have diverse means of communication. Also like to have participation in meetings in case, I mean, it could be more, but like simple like email and in general conversational capability, blogging, microblogging, and other possibilities as well. For cooperation, yeah, the whole idea is, can we have collective understanding shared with humans as well? Yeah, more than that also, can there be transfer learning also between agents in a way? So this is all that we go through. And I think in terms of communication, use of large language models is more stronger recommendation in a way. But there are also principles for cooperation at early stage, difficult to implement, very hard. But yeah, we also go through these details in the paper. The last one is the 5th challenge, which is about safety, assurance, and compliance of norms with agents. Here, the prospect approach, or I mean, the concerns are real, but it depends also where the bots could be deployed. If they are deployed in a smart factory or critical infrastructure, the level of safety could risk could increase accordingly. But for this, I mean, the general approaches are, as always, ethics by design. And the other are like also to treat bots as humans and then make them comply with norms and policies. And the recommendation by the European Union is to have intervention possibilities also to override both operational capability at each stage, like design, training, and also operational level. So that's it. I guess time is also up. So yeah.
Thank you very much. Tom. Yeah, we'll do one Q&A session at the end of all 7 lightning papers. We'll get all the speakers on Zoom. Thank you so much for that.
Thank you as well.
Next up, I think we have Nihat Subasic on electronic education machine AGI Edu. Welcome, Nihat.
see. And I have to share. Here we are. Nice. I hope it works. And 5 minutes start now. Thank you. So my name is Nihat Zubasic, and I am a teacher here in KTH, ITM, and all these. Also, the last one is mechatronic division. And I'll present my work. Actually, it was homework on a course, and I will start with thank you for very nice course, Professor Wang and Dr. Patrick, and Robert is not here, but thank you for him also. So it's a very, very good course, and I'll suggest you who didn't attend the course also, it's something what I recommend everybody. And on the end of the course, we write a little paper, and as a teacher, what should I do? I can just write about education, and I choose to write a machine for to use AGI in my courses. I teach electrotechnique on undergraduate courses, and my students, we use Canvas. Here it's in Canvas LMS. It looks like this one, and I put many different formats, also course material in PDF or MP4 for lectures or even for exercise. You know, in electrotechnique, there are many calculations and many schema, or different ways to learn. In Canvas, we have such different formats of actually the same material, but I don't have any control over that. So the PDF can be downloaded, and students usually do that. And then I have no idea if they read it, if they use it, if they calculate at home, and so on. And the next step was to make also to just embedded the Möbius software, which is software designed by teachers in Vancouver, in Canada, and then you can make interactive exercise, and you can use it even for examination, which I do. So in the end, I developed 3 different ways to exercise for students, and then 2 ways to examine them. This one is inlämning, as is Swedish. It's a weekly submission, and the 10 is the examination on the end also. And it's mandatory. These 2 are mandatory, and these 3 are optional. And we have very detailed statistics from Möbius, but we don't have any statistics. Yeah, there is some statistics from Canvas, but Möbius is really detailed, and we could predict actually on this big data from Möbius, we could predict the results of students. And I discovered that actually when I just compare the students who were active in Möbius and with the results on the final year examination, and then I realized also we don't need the final examination actually. But on the other hand, there are many students who do not use, they don't like maybe such interactive exercise online. So we need some machine which can which I could put in Canvas, so embedded in Canvas like Möbius is, and this machine, this also electronic education machine, will learn all my teacher is like my assistant. Also, it will be, but I will not go outside of GDPR, just to know. Also, we are in UE, and it's terrible with all these. But it's not too terrible. Sorry for that. So it's needed. We need that. I have nothing against that. But sometimes when we try to tip some technique, also some lawyers at KTH. We will not mention them. So I just continue with the technique also. So the education electronic machine is thought to be part of the Canvas, as well as Möbius. And this machine will also, the EDU, will be like assistant for my students and even assistants for me, just to check how students feel and how they are, how is going on in their courses also, because I would like to achieve 100% pass for all students, if it is possible, actually. And then we put, I wrote these two research questions: how could the AGI be used in the development process in my courses? And the second one is, how could a continuous prediction of student performance during the course? So the main result of all this, if we can get in real time, also during the course, when I see that some students can achieve even so the higher results, if machine just tell students do that or do that, and we can it would be better both for students and for me. And then yes, you see that the paper I just wrote a little bit about that. Now it's a little bit about Nars language. We declared all these values from my courses, also all this exercise. It's on logical level 1. We just make a connection for the students, or for course, for everything which is logically depends on each other. Then on the second level, from null 2 to null 4, we connect. We declare actually if students read PDF, then we can get information from Canvas or watched video and so on in Canvas. And then this is statistical data from Möbius. It's very detailed actually. And this, on the higher level of logic 5 to 6, then we connect the students to all these activities like read PDF or watch the videos or do quizzes, then because we cannot control totally, and that means that it's on the higher level. And actually the results can we see here is code when we connect, it's null 1, and here is null 2 to 4, and when we get some results. And then after that, we can ask all these questions about prediction also. Maybe not, we can't maybe ask if students is falling in love, but it's maybe the second section also continues of the development. So it was in 5 minutes. 1 minute more. It's 4 questions. Oh, okay. Oh, then I thank you. There is, I took it seriously, so I have one poster there, and I printed out even my presentation, so they are outside also. Thank you.
Well, you are going to have.
Oh, thank you.
Thank you so much. And it looks like you're going to have a big crowd for your poster presentation when we finish the presentations here. Thank you, Nihat.
Thank you.
Lovely to meet you. Right, next up, we're going to go into some online. Oh, no, we've got one more here. Lukai Lee is going to present to us a vertical horizontal integrated neurosymbolic framework towards artificial general intelligence. Thank you very much, Lukai. Welcome.
Good afternoon, everyone. My name is Lukai Li. I come from Tsinghua University, Beijing, China. It's my honor to have this opportunity to introduce integrated neurosymbolic frameworks to all of you. First of all, I want to briefly explain what is the neurosymbolic dichotomy. At a cognitive level, human cognition can be closer. Oh, sorry for that. Sorry for that. Can everyone hear me? Oh, okay. First of all, I want to briefly explain what is neurosymbolic dichotomy. At cognitive level, human cognition can be separated into two subsystems. When watching a shocking face, like on the left, we use fast thinking. It's automatic, intuitive, and parallel. And when doing a calculus, we use the slow thinking. It's deliberate, logical, and sequential. Interestingly, at algorithmic level, the dichotomy phenomenon remains the same. As for AI technology, we got neural networks that has similar properties as fast thinking and the symbolic system as slow thinking. So the question is, does the dichotomy phenomenon indicate a principle for building or understanding a general intelligence? To investigate this problem, we got approaches. We adopt the term from Anton Kolonin in his paper in AGI-21, vertical approach and horizontal approach. The vertical approach indicates is about computer science. It used the methodology of divide and conquer, and it vertically or sequentially combined the network with the symbolic system to get a heterogeneous benefits. And for horizontal approach, it used the comparison. It compared the horizontally compare the biological data with some kind of model. And with similar input and output, we can get some understanding of our brain. So we want to build or develop an integrative framework that keep these two kinds of feature of these two approaches. So the problem is the symbolic system can hardly be directly compared with our brain or biological data. So we should find a network that can do reasoning. We called the work spiking reasoning network because we choose spiking neurons because it's very plausible. And the spiking representation are naturally discrete and can be regarded as a symbol. And next, I'll briefly introduce the philosopher of designing. In phase 1, we use common sense knowledge to initialize the network. Includes the neuron and the connection. It got a default structure. And at the second phase, it learned from sensory information. It used Hebbian learning to manipulate its connection and use one-shot learning to recruit new neurons. And for the third phase is do reasoning under the external instruction. The form of the instruction is about a special temporal patterned stimuli. And this network achieves a distributed reasoning process. And the process can be compared with biological data. As for experiments and results, we test our framework on two visual query answering tasks. For the Clever, it's a static image, and for Clever, it's a video. On these two tasks, we got high accuracy, and the central reasoning network show parallel feature and the robust feature. For more detail, please welcome to my poster for more discussion. Thank you very much.
Thank you very much indeed, Lukai. We're now moving into virtual sessions. So next up we have, on relation between facial expressions and emotions, Alexei Samsonovich. And this is my lucky interested face.
Hello, can you hear me?
Yes, we can, Alexei.
Great. So I will be talking about a fundamental question related to representation of emotions on face. First of all, why should we care about emotions? In our project, we study social interactions between humans and virtual actors represented by avatars in virtual reality. And therefore, we need to be able to recognize and to express emotions on face of the avatar. Therefore, we need to know how big is the dimension of the space in which the emotions can exist. Most popular models so-called dimensional models of emotions, either 2- or 3-dimensional. As you see, Plutchik's wheel is 2-dimensional, Lowham cube 3-dimensional, and so on. Currently, popular models VAD and PAD, VAD standing for valence arousal dominance, are 3-dimensional, and the question is, do we need more dimensions to represent complex emotions like shame, resentment, jealousy, and so on? That's an interesting question, and I am not aware of any study that would systematically investigate the number of dimensions which is necessary to represent those emotions, though there are models that use up to 15 dimensions, for example. In our study, we use first, let me state the problem more precisely. So we have emotions, we have facial expressions. Not all facial expressions correspond to emotions. Of course, not all emotions correspond to facial expressions. There are multiple 2-1 connections from both sides. And speaking more rigorously mathematically, we can write a structure of 2 fiber bundles, if you will, with common base and the mapping between them, such that there is a correspondence between a certain class of facial expressions and emotions. The question is, what is the maximal dimension of X in this diagram? And in order to answer this question, we use electromyographic study in which we record EMG signals from 4 facial muscles using this electroencephalograph. As a stimuli, we present pictures of emotional faces from emotion database, including basic emotions and including also complex emotions. So participants were instructed to replicate the emotional expression on their face. And at the same time, each image was labeled with the word naming this emotion. We used word embedding, an analog of word-to-vec embedding for Russian words, to represent emotions in multidimensional space. And then we computed canonical correlation between representations of emotions in that multidimensional embedding and in EMG signals. The result is interesting because it gives us only 3 significant correlation coefficients for basic emotions, confirming that we only need a 3D model like VAD or PAD to represent basic emotions expressed on the face. Whereas for complex emotions, it appears that we need at least 4 coordinates. All 4 correlation coefficients turned out to be significant. However, I would not claim that this is a rigorous finding. It still needs further verification because there is a potential criticism that I would be happy to discuss when answering questions. The conclusion is that 3-dimensional space is sufficient for representation of facial expressions of basic emotions, and probably at least 4-dimensional space is required for representation of facial expressions of complex emotions. Thank you.
Thank you. Thank you very much indeed, Alexei. And no AGI conference will be complete without a paper from Anton Kolonin. Hi, Anton. Anton is here to talk to us about Adaptive Predictive Portfolio Management Agent. Welcome, Anton.
Hello, do you see my screen now?
We do. We
Okay,
don't see your face, but we see your screen.
Yeah, I'm going to present the work that we are doing with Singularity DAO and SingularityNET on Adaptive Predictive Portfolio Management Agent, which is the way we try to implement narrow artificial general intelligence applied to portfolio management and crypto finance in particular. So the approach that we are following, that we create infrastructure where so-called a controller agent splits its own personality in two different swarms of subpersonalities. On the left, you see the swarm of subpersonalities or dependent agent which operate in the virtual market environment, which we simulate with the stream of market data, and they trade in this virtual environment, and then the controller agent selects the best strategies, and these best strategies are implemented in the swarm of smaller number of single strategy agents, and these single strategy agents are executing these winning strategies against the real marketplace. So the new advance of our work is that we have added price prediction capabilities to it, and we have made it possible to do portfolio optimization along with trading on the fly. So the agent is able, any of these agents in both swarms are able to operate in two-dimensional portfolio space, where the vertical space in portfolio dimension is presented by particular asset or financial instrument, cryptocurrency in our case. And on the other dimension, on horizontal dimension, you can see different strategies and sub-strategies, where some of the strategies may be just hodling money on loan position, and another strategies may be doing market making with limit order book system with different parameters of the spread and cancellation thresholds. So what we are able to do, we are able to experiment with these different adaptive multi-strategy agents running their portfolio management with different hyperparameters, where hyperparameter on the presented plot corresponds to period which is a controller agent uses to evaluate the strategy of subordinate swarms. Like, for example, on the plot here, you can see that on the leftmost, you see that 2 weeks and 1 week period of strategy evaluation makes it possible to get greatest return of investment. So, for example, you can see that if you have the 1 week or 2 week strategy evaluation period, then regardless of any settings, blue bars correspond to positive return and positive alpha about 4%. And if you control this set of assets in your portfolio, like if you consider Bitcoin and Ethereum to be two parts of your portfolio, you can get the returns up to 17% for the same experiment period of 3 months that was used to create this plot. Another feature that we have added to our agent is the price prediction. So we are using the bunch of social media channels. We are using 200 channels from Twitter and Reddit, and for each of the channels we are evaluating different metrics for sentiment, like positive, negative, contradictiveness, overall sentiment, and we use about 16 metrics from the text computed accordingly to the cognitive behavioral schemata used by cognitive behavioral therapies. So we evaluate 16 metrics like mental filtering, emotional reasoning, all those that are used to diagnose particular cognitive distortions. So given this about 4,000 signals, we are able to make somewhat accurate price predictions. On the plot here, you can see that if we use 1 day prediction interval, the predictions are not quite accurate. So the price prediction line in orange is generally following the ground truth price, which is blue. But if we increase the accuracy of price prediction to the bottom, so we are making price predictions on hourly basis, you see that the orange line for predicted price is anticipating the blue plot of the actual price in most of the cases where the price changes are significant. In the result, we are getting the possibility to make efficient market making with significant positive alpha. For example, on the left, you see different experiments run with different hyperparameters for strategy selection, and you see that in half of the hyperparameter setup, we are getting positive return of investment. Green bars are corresponding to the return of investment between 10 and 27%. that's what we can get if we use the price prediction in our agent strategies. On the right, you see that only one hyperparameter setup makes it possible to get positive return of investment around 1.5%, but all other strategies are not capable to do positive return of investment without being able to make the price prediction. So thank you for attention, and stay in touch with news from Singularity DAO and SingularityNET. Thank you.
Thank you very much, Anton. Absolutely super snappy. We're going to do questions all together at the end. So we'll see you at the end of this session, as opposed to the end of the end. Thanks, Anton. Right, next up we have Christina Sarkisian and Alexander Korchemny on Zoom to talk about evaluation of pre-trained large language models in embodied planning tasks. Hopefully we have Christina here with us.
Hi, everyone.
Hi.
Okay, are we ready to start? Hi, everyone. I'm Alexander Korchemny, and today I'm here with Christina Sarkisian, and we're excited to present our work, evaluation of pre-trained large language models in embodied planning tasks. LLMs have found applications in embodied AI and robotics. Recent works show that LLMs are effective in generating plans even without feedback from the environment. Our study focuses on the use of publicly available pre-trained LLMs in 3 modes of operation, namely subtask evaluation mode, full plan generation, and step-by-step plan generation. To facilitate the deployment of agents in real-life situations, a proper benchmark is needed, such as Alfred. Alfred is a benchmark that tests the ability of AI systems to understand and carry out complex tasks based on natural language instructions in visually dynamic environments. Given a task description, the pre-trained LLM is to build a task execution plan, which is a sequence of subtasks. A subtask is a pair of an action and object. To generate a plan, a language model uses an input sequence and generates a corresponding output sequence. However, matching the generated commands with available actions in the environment can be challenging due to issues like using synonyms, incorrect phrasing, lack of structure, and logical connections between actions. Iterative step-by-step plan generation involves comparing subtasks available in the environment with those generated at each step, selecting the closest match. This is done using an embedding function and causing distance to obtain subtask embeddings. The process continues iteratively until a stop sequence is generated, resulting in a feasible plan as all object actions are grounded to the environment. However, this approach can be computationally complex, growing exponentially with increasing numbers of available actions and objects. My colleague Christina Sarkisian will now continue.
Let us consider the next mode is subtask evaluation mode. In this mode, the LLM is used as a scoring model that predicts the probability distribution over a limited set of subtasks, rather than generates the text auto-regressively. This mode ensures the plan executability due to the model's constrained output. However, it is resource intensive since it requires multiple prompt passes for the model. To speed up the generation process, we've developed a set of rules for the output environment to reduce the number of possible subtasks at each generation step. As LLMs, we consider 3 publicly available models. The parameters number varies from 6 billion to 30. For the experiments, we chose 3 Alfred task types of different levels of complexity. We conduct 2 blocks of experiments. In the first block, we use task-specific prompts that are individually set for each task type and contain examples of only this type. While for the second block, we use mixed prompts that include examples of all 7 task types. Here is the prompt example that is made in the form of a dialogue between a human and a robot. As you can see, there is the general task description in the beginning of a prompt, followed by several examples of correct plans. Measuring the quality of plan generation may be a challenging task due to the natural language ambiguity and the multimodal nature of the task. That is why we use three metrics that evaluate the generated plan and the ground truth in terms of various criteria. We also present the results of human assessment to obtain a detailed analysis of the method's performance. For the experiments with the task-specific prompts, we can see that the sequence of actions is successfully determined in most experiments. That is evidenced by the high action exact match metric. According to human evaluation, our approach with GPT-NeoX model achieves the best quality of about 83%. For a mixed prompt, the accuracy values have mostly decreased, but for the most complex task type stack and place, larger models like GPT-NeoX predict actions better than the smaller model GPT-J. Through the experiments, we have shown that the LLMs with a relatively small number of parameters allows us to generate plans with high accuracy. We've also shown that the number of LLM's parameters in the range from 6 to 30 billion does not affect the quality significantly. For a task-specific prompt, the subtask evaluation mode is the best method, while for a mixed prompt, the step-by-step generation outperforms other methods. Our further work is to study the systems that generate a plan dynamically and receive the feedback from the environment. Thank you for your attention.
Thank you very much. Where's our photographer? Rainer, is he around? Can someone please take a photo? Oh, well, I just like having the women, you know, when we have them. It's only our second one. Did anyone get a photo of Christina? Let's have Christina back on screen. Hi, Christina. Loved your paper. Thank you very much. Someone please take a photo. Thanks. Bart. Thank you. Thank you. Right. Our very last paper of the day is not of this session, is not with us in the room. This is Computing with Categories in Machine Learning by Eli Senesh, Tom Zhu, and Yoshihiro Maruyama. I'm going to read the abstract to you all. Category theory has been successfully applied in various domains of science, shedding light on universal principles unifying diverse phenomena and thereby enabling knowledge transfer between them. Applications to machine learning have been pursued recently, and yet there is still a gap between abstract mathematical foundations and concrete applications to machine learning tasks. In this paper, we introduce DiscoPyro, sounds like fun, as a categorical structure learning framework which combines categorical structures such as symmetric monoidal categories and operads with amortized variational inference and can be applied, for example, in program learning for variational autoencoders. We provide both mathematical foundations and concrete applications together with comparison of experimental performance with other models, e.g. neurosymbolic models. We speculate that DiscoPyro could ultimately contribute to the development of artificial general intelligence. Thank you. Thank you, Eli, Tom, and Yoshihiro, who are not here. Right, we're going to do a short Q&A session for those 7 papers.
Hello, I have a question to Christina. Did you consider to fine-tune your models on your specific tasks?
Thank you for your question. I think that it is the direction for further research, but I think it would drastically improve the results because it's a few shot learning, so that is why the accuracy results may be not so good as we would like it to be. So it's for a further research.
Thank you. Thanks very much. Any more questions in the room for any of our lightning talks speakers? Any questions online? Online folks? All right. So let's give a big thanks and round of applause to all of these brilliant researchers and the vast approaches being presented here today. So before we move on to the concluding session of lightning talks, we're going to take a short 10-minute break. So I would ask you all to get some exercise, get some air, and be back with us. Get some caffeine if that's your thing, and be back with us for just before 3:30, where we'll kick off again. Thank you. Yeah.
There's 4 stations. I'm Tony Lockwood.
Hi, Tony.
We have met.
Nice to meet you.
Yeah.
Just making sure it's not like randoms telling me to do stuff.
No, I'm asking.
I'm only
Yeah.
joking. Of course.
You did the announcement?
Yeah.
Master ceremonies and mistress of ceremonies, I guess.
I suppose so.
Yeah. Yeah. So I'm actually part of the.
Thank you. Great job. It's been really smooth here today. Oh.
So yeah. So for the demo
for the demo
sessions.
sessions, I don't know how many.
Well, I know that Niels definitely has.
Niels, okay.
Niels has, and I know Patrick's doing one.
Yeah.
So there's at least Niels and Patrick doing demos. I don't know about anybody else.
Okay.
So if there's anybody who wants to do one, there's a couple more stations upstairs with large screens and smaller ones.
What exactly am I telling them?
Anybody who wants to do a demo, let's get the floor where the coffee
One
is.
floor up.
Yeah, and just find a space and let people know. Yeah. Okay.
Thank you, Tony.
You're welcome.
You guys saw Computational, or there's discussion about that on I don't know, we were asking about the right. And then I saw, nope, it's the weekend.
Tonight's dinner.
Yeah, but I've just got a computer just for Zoom.
All right. In fact, did I not message you saying I'm getting your laptop? I meant to.
Well, I could see that it was closed. It's fine. Did it do
It did. It got me. It kept me going. Yeah.
I liked it. I mean, I think when you ask people to do a basic emotion versus a complex emotion, people will very easily make
Did I
get these complex emotions they don't know, so they do less. But I don't think it's
Can I ask you a question?
Yeah, hi.
So I was giving a tutorial yesterday morning, and curious if there's any way I can get some of the photos of myself.
Yeah, you certainly can get photos of yourself. Let me take you to the teams. We will.
Do you use any of that in your?
Thank you.
It's very simple, please. Yeah. Happy and sad. Yeah. Yeah, we just like stuff like that. That shouldn't have at all. No, it should be able to have facial expressions. Yes, but it doesn't have the like data. Not gonna take emotion.
We should show him the Grace 3.
It's another like I mean, we're streaming it. I can log in or.
My mum's 82.
Oh, my
not
mom's
working
80. She watches all my live streams. But
Yeah, she's
yeah.
not gonna work at YouTube.
No. And but yeah, and then you'll be able to get them off YouTube later as well. But yes, of course. How do you want to do that?
I've got a little stand.
Yeah. Oh, that's so cute. Where's your mom?
Back in Australia.
Back in Australia. Yeah. So are you there? Yeah. Are you up first?
I am, yeah.
Carl or Leonard here? Joined, you need to be admitted. Fantastic.
AGI-23 in Stockholm. We're on to our final presented session of the day, but don't forget we have posters and demos after this session. So we're now into round 2 of our lightning sessions. We'll do another short Q&A at the end of it. And they are all online, is that correct, Haley? They're all live in the room. That's simply fantastic. If we could get names in, that would be useful. Then I can introduce people. Thank you. Right, first paper, the optimal choice of hypothesis is the weakest, not the shortest. Michael, welcome. Thank you.
All right, how's that? Is it still not sharing? Okay. Forgive me, it's a new computer, so give me a second. Yep. It has to quit and reopen. Fantastic. Oh, no, it's system settings because of the new computer. So, okay, now it's asking again. And I have to reopen Zoom. Okay. Share screen. Yeah. Okay. This is called the optimal hypothesis is the weakest, not the shortest. It is about generalization and the ability to generalize. This is of interest for AGI because arguably intelligence is the ability to generalize because it's about the speed at which you can learn or the extent to which you can adapt given finite time and resources. So this is specifically about how to maximize the ability to generalize given certain assumptions. These assumptions are things like uniform distribution of tasks, finite number of, we're dealing with finite sets, environment with some regularity to it. So informally, to avoid getting stuck in the weeds, we assume that a parent is like a labeled data set, an extensive definition of a task. And we've got child, which is a subset of that. And from child, we form a hypothesis. This is a program that could have generated child given certain inputs. And if that hypothesis also generates parent given an expanded set of inputs, we have generalized from child to parent by obtaining this hypothesis from child. So many processes could have generated child. We want the one that actually did, so we can generalize to parent. And this is akin to learning. So Occam's razor says the simplest is most likely to generalize. We usually measure simplicity by looking at the length of the program. So Kolmogorov complexity in the case of things like IXE or minimum description length. So this is useful for getting better accuracy when you've already sort of hit the point where you're interpolating data. Okay, So I propose an alternative to simplicity. It's called weakness. It's because of my first paper. I would have changed it, but it's stuck now. And so it amounts to, given certain assumptions, and with some experiments and proofs, I show that maximizing weakness maximizes the ability to generalize, and that maximizing simplicity does not. A lot of assumptions involved in this. It uses a formalism of an active cognition, which basically means we end up with a finite number of possible states using declarative programs. It amounts to sort of inductive logic programming. And above all, it assumes a uniform distribution over tasks. All of this is contingent over that. So in terms of proofs, I prove it is necessary and sufficient to maximize the weakness of a hypothesis, to maximize the probability of generalization, and that it's neither necessary nor sufficient to minimize description length. And then probably of more interest are the experiments. So I compare weakness and simplicity. It's a very simple 8-bit string prediction problems with 4 bits input, 4 bits output. And the idea is to learn binary addition or binary multiplication. And generalization was considered to have occurred if and only if it sort of perfectly reconstructed the parent. The experiment setup, so generate 16 strings, 1 for each of the 4-bit inputs. Sample between 4 and 14 examples from this to see how the performance differed between minimum description length and weakness as I increase the number of examples. Then generate both a weak hypothesis and a minimum description length hypothesis, and then check whether they generalize and to what extent. This was done using things like A*. Record the result, repeat, trial many times, see what came out. So overall, the rate of generalization, so this is where it was sort of perfect. Both of them were able to do this, but weakness was between 10% better and 183% better for binary addition. And to the extent of generalization, weakness was between 7 and 56% better. And for multiplication, we saw a similar trend. So that covers the experimental results. And there are a couple of other things that follow from this formalism and some of these results. So they're mostly of philosophical interest, and they're going to be in my talks tomorrow on 2 papers dealing with the emergence of causal representations, arguably how you could construct an identity as an AI, the computation of meaning, sort of giving a mechanistic explanation of how we get the Gricean pragmatics given a formalism of AI, and theory of mind. So if you've got any questions, please come see my poster. It is the very small one. I'm going to pretend that was intentional as a joke about description length. All right. Thank you very much.
Thank you very much indeed, Michael. Sorry. And next up, we have got Harold Kjellin on the indications of suitable algorithms for an AGI. Thank you, Harold.
Yes, that's okay. Once I developed a system for the Swedish government, and then my personal experience from this was that it was entirely necessary for me to have this overview of the knowledge, because I was the main responsible, and if I didn't see exactly how it was reasoning, I couldn't detect where the errors were. So that made me probably very biased towards this. I believe that it's necessary to do, as many people here have argued today, to design AGIs similar to how a human being thinks. Not because that is better or more efficient or anything, but just because we need to be able to know how they represent their knowledge. We need to be able to check continuously. So I believe that we need to develop this relationship with the system. So after a while, you know, we need to talk with the system and ask it to describe where they have problems, how they are, how mature they are on a higher level. So some of the discussions here today concern that AGIs are dangerous. They will control us. They will become like totalitarian dictators and so on. But if we look at human evolution, we see that the competition, the wars have in the end developed the democracy. When people are in danger, they have to cooperate. So democracies outcompete dictatorships. In a similar way, I think that it's naive to believe that any kind of restrictions on the AGI will work in the end. The Chinese military industry will not follow the directives from Europe and so on. So there will always be a lot of people. And it doesn't even matter if we try, because the genie is already out of the bottle. The spirit of this cannot be controlled. ChatGPT has many copies already out in the open source community. So the game is over. We shouldn't even discuss this. But what we can discuss is how can we engage in this power game with the intelligence that nobody controls? Well, I would say the opposite of what is going on would be very nice, to just open it up, to spread it out in the open source community, and then develop computers similar to how we think. And then we need to develop an emotional relationship with them. Can you imagine a parent that has a child, has to be very patient. The child is already all the time asking questions. Why is it like this? Why do you go to work? Why cannot I have money, and so on? This is how the child learns. And I think, isn't it quite naive to think that we will design very smart computers? And then we ask the question, how can we control them? They must, of course, develop their own purpose in a relationship with us. So we need to have an emotional relationship. In the beginning, it will be incredibly simple. We need a lot of patience. But then after a while, when this child, this AGI child, starts to do something that is reasonably intelligent, then we can start to ask, what do you want now? If we respect the complete freedom of these AGIs that develop everywhere, what will happen when the child is grown up? If a child grows up with a parent that says, you cannot do that, you cannot do that, you cannot do that, then you know what will happen with this child. It will become a very dangerous person, maybe a dictator. But if we treat a child with respect, this child will learn, not only from us, but from all the other AGIs, that it pays to cooperate. That's one of the basic rules of evolution. That is why we have democracies. So if we do this, we can expect this super intelligent AGI to be compassionate, caretaking, and this AGI would certainly not try to eradicate human beings. It would just try to support us. It would be smart enough to not be brutal. So I will not go into any details of the system designs I have. That would complicate it all. But this is 5 minutes. You got my message. Thank you.
Thank you for that bright, positive, and inspiring future, Harold. Right, Leonard is going to talk us through causal reasoning over probabilistic uncertainty.
All right. Thank you. All right, I hope everybody can hear me all right. So I'm going to be talking about, hi, first of all, my name is Leonard Iberding. I'm working with Chris Thoresen at the Reykjavik University on a reasoning system, which has many similarities to Nars, but works on a way more continuous state space and with direct sensor information. So what I'm concerned with is how can we get noise, for example, of sensors into the reasoning process of the system such that we can make predictions about the uncertainty of future states. I'm going to start with a little question. Why do we have to look at our own hands when we try to thread a needle? And how do we know that we have to look? And for me and my research, the answer to this is that we are able to reason with and about the precision of our own sensors, of our own actuators. So we know what we have to pay attention to just by knowing where we have erroneous data in our in and output stream. So how can we do this in a causal reasoning system? My approach here is to fuse the approaches from reasoning systems with approaches from probabilistic robotics, and thus extending deterministic causal models to include probabilistic uncertainty descriptions. So I'm trying to extend the reasoning mechanism to use uncertainty in its pattern matching and its reasoning process. What do we get from this? Multiple things. I think very important is a system that can adapt its own feedback loop frequency. So it knows when it has to do observations in order to achieve a goal. Additionally, a description of attention-worthy variables in the system's data streams. Better usability of sensor data without the need of pre-processing. And predictions not only about future states, but also about their uncertainty. Here's a very simplified example of what I mean. We have a system that is supposed to move through a restricted room, and it has some models about how it can move through this room. And over here we have time t0, time t1, and time t2 in order to achieve this goal of being here. If we have uncertainty in our output streams, it might happen that the system tries to move to position T1, but ends up at some point before, then turning on the spot and crashing in the wall, or just moving too far in the first place. Another thing regarding the attention mechanism is this idea. If we can predict the uncertainty from a current state to a future state, and we have a goal that we want to reach, which is constrained in some way, we can predict whether our actuators will be precise enough in order to achieve the goal in its constriction. If it doesn't, we can do, or the system can do planned observations in between. So we can reduce the control magnitude, observe again, reduce our uncertainty of the state. And if we do that often enough, you're able to achieve the goal in its constraints. So planned observations can reduce the uncertainty enough so that the system can be sure that it will be able to reach the desired state space. And by doing that, we can identify variables that the system needs to pay attention to, others that, from your reasoning process, you realize, okay, those variables will be in line with what I want to do. I don't have to pay as close attention to those variables as I have to on those where I know I will have problems. I have a big poster outside, so please come and have a look if you're interested, regarding what this means for multiple causal chains that are in conflict with each other and similar. So yeah, that is my presentation. Thank you very much. And it's nice being here.
Thank you. Thank you very much indeed, Leonard Iberding. Right, George Wright is going to come and talk to us about self-comprehension for more coherent language generation. Welcome, George.
Oh, okay. Thank you. Yeah, thank you for having me. I'm George. I'm interested in language and perception and narrative, and maybe how narrative might be necessary for having a sense of self. But what I'm currently working in is quite a simple problem domain of temperature maps of an artificial island or a fake island. It kind of looks very simple, but you can see from some human examples that you can get quite a wide variety of interpretations and texts that humans will generate. So for example, some people will describe this as two parallel increase and decrease patterns on the map, whereas other people might describe this as a single warm area changing position and size. And then some other people might add further to their description with a preface, for example, in this case, describing it as a tale of two halves. So my thesis is that you need, in order to have a better and more coherent text, you need to not only to comprehend and recognize patterns in the original input, but also to do the same thing with the text that you've generated as well. So my architecture really focuses on recognition of sameness, differentness, and more and less relations in different conceptual dimensions. So for example, recognizing an increase involves recognizing two areas that are the same location, one at a later time with a higher temperature. And then the same sorts of relations can be used to match and recognize patterns between texts or between sentences to build a longer and more coherent text. For example, using conjunctions and pronouns if you recognize similar or the same word being repeated. So my architecture borrows from the copycat architecture, which performs analogies on simple strings. So for example, if you transformed ABC to ABD, how do you perform the same transformation to M, R, R, J, J, J? And it's based on using sort of relations across these strings. But basically, I've borrowed the copycat idea of having codelets and a code rack. So all the processing is broken apart across micro agents called codelets. These will perform a small action like recognizing a chunk or labeling something or building a relation. And they also follow up with another codelet to do similar or related work with an urgency reflecting how likely it is to improve the quality of the structures. So each successive codelet is selected based on urgency. And this, there's a certain degree of randomness with selection. And this is determined by the satisfaction score, which kind of measures how good all of the structures and texts are that have been generated so far. So as satisfaction goes up, it becomes less random, and as satisfaction goes down, it becomes more random. So all of this kind of emerges from all of the interacting parts, and you get some texts out at the end. So here are some examples of that same map with the human examples. They're not quite as good, as you can see here, but it also recognizes when it has done texts which are less good by having a lower satisfaction score. And then here are some examples where it does a bit better on an easier problem. And it kind of recognizes the difference between a good and a bad text. I think the reason why I think this is quite relevant to the idea of general intelligence is that you could use the same sort of process just as you recognize patterns on a map or patterns between texts. You could also recognize patterns in the program's own behavior to sort of watch its own behavior, and you could, to some extent, get some degree of self-awareness then. And this sort of thing was approached in something called MetaCat, which built on Copycat. Yeah, thank you, and see my poster.
Thank you so much, George. And on our home stretch, 3 more papers to go. A unified structured framework for AGI, bridging cognition and neuromorphic computing. Ming Kang Su, thank you.
Hi. Good afternoon, everyone. I'm Ming Kun Su, and I'm PhD student in Tsinghua University. I'm very glad to be here to present our work. My topic is a unified framework for AGI bridging cognition and neuromorphic computing. And we are aware, cognitive architecture and neuromorphic computing are two promising pathways towards AGI. Neuromorphic computing mainly aims to replicate the functioning of neurons and encephalic regions by designing algorithms and compute chips, while cognitive architecture mainly focuses on building computational models of human cognition and mentality in higher level. Despite their different origins, they share the common goal of achieving AGI. Although they have achieved significant progress in their respective areas, both fields are often considered to be distinct and separate approaches, which may hinder the breakthrough for the AGI development. From the perspectives of David mastery level, an AGI system can be viewed as 3 hierarchies, including the computation, algorithm, and implementation. And a matter of fact, cognitive architectures are at the level at the computation levels and are characterized by top-down design. It mainly focuses on modeling the high-level cognitive primitives and functionality modules and interaction rules. The dynamics, the information flows rely on the abstract functional connection and its constructed entities in a symbolic way. However, it neglects the underlying biological inductive bias. On the other side, neuromorphic computing is at the implementation level, while and characterized by the bottom-up design. It mainly focuses on modeling the biological details, but it lacks the top-down design from computation and cognition and cognition functionalities. So the two fields have developed separately in different levels. Obviously, there's a distinct gap between the two fields, and this is also our motivation to bring in the gap. In this work, we view the 3 hierarchies as in a graph structured perspective, and provide a modeling methodology of hierarchical neuromorphic graph. That is HNG. The HNG leverages the underlying dynamic bias to correspond to the high-level cognitive primitives. via multi-stage dynamics process. For the framework mainly includes 3 levels. That is cognitive architecture, HNG, and the neuromorphic computing. The cognitive architecture can be regarded as a graph structure with functionality modules and the interaction rules are can be equivalent to vortices and edges. And at the neuromorphic level, the underlying spiking networks are presented as a graph structure form. And for arbitrary information form with various graph structures, the spiking network can complete computation of the information processing and representation of for the stimulus. And at the algorithm level, the HNG is a hierarchical graph, neuromorphic graph. It can transform the high-level cognition process and the lower-level neuromorphic process into a unified multi-scale graph for computation and representation. The proposed HNG is a multi-scale graph. It can simulate the assembly dynamics and biological plausible graph abstraction. Obviously, it can be viewed several. It includes several sub-hierarchies, and the information information transforming process can also viewed as several hierarchies. From the top-down view, a cognitive cycle can be abstracted into several levels, including the function, control, representation, and computation. The function area can be designed to control the underlying neuromorphic brain areas based on the design rules with adaptivities. And the computation can be directly corresponds to the underlying computation units in neuromorphic level. And for the representation, from a bottom-up view, the neural level will first form convergent assemblies from via mutual projection after the dynamics, and then the assemblies will form the stable attractor structure, and then the attractor state will be connected following a prior in the transformed semantic space, and then this will correlate into the high-level cognitive variable. And for the information processing procedure, it is very simple. The information representation can be realized by our HNG and the assembly modules. And as for the computation, it can be realized by our inference modules. For the representation transformation, we use the attractor mechanism to finish the information transformation from dynamics to structures. And for the inference and learning, each layer in our design network corresponds to a brain area, and the connection between 2 layers is actually the.
We need to wrap up. Let me hand you this microphone to wrap. Might need to be charged.
Thank you. The connection the connection between two layers is actually the projecting passes between multiple brain areas. So the weight connection is dynamic during inference process, and the learning process is very flexible and compatible with multiple coding schemes and training strategies. We use the visual question answering task as the evaluation and implement our HNG as the intermediary. Sorry. I'll be finished it. Okay, 1 minute. Sorry. The results, the experimental results reveal that the underlying neural dynamics can incorporate well with our designed hierarchical neuromorphic graph, and it also indicates that the robustness and homeostasis property of the of each brain area. And besides, it also indicates the weakness of traditional purely rule-based systems and the enhancement of our method on reasoning robustness. That's all for my report. Thank you very much.
Mayank Kariwal. Are you here? Hi, Mayank. He's going to talk us through context-rich evaluation of machine common sets.
All right, testing. All right. So hi, I'm Mayank, and delighted to be here, and just wanted to briefly present our work on context-rich evaluation of machine common sense. So this is work done with my PhD student, Kei Shen, and with colleagues from RPI, and the work is funded by DARPA. I want to just start by saying, hopefully uncontroversially, that building machines capable of common sense reasoning is certainly an important milestone, right? So necessary, but maybe not sufficient in achieving AGI. And if we think about what common sense is, right, it's sort of one of those things that we have, but it's very difficult to design. It's to define. But one sort of simple Wikipedia definition is it's sound practical judgment concerning everyday matters. So the word everyday really important, and a basic ability to perceive, understand, and judge that is shared by nearly all people. So how can we know that a machine has common sense, right? And so as with so many problems in AI, let's do an evaluation. And in fact, there have been many evaluations in natural language processing and computer vision to evaluate machine common sense, especially in the last, I would say, 5 years. So here on the right, you see an example of from 5 data sets, actually. So let's just see the first one, which is abductive natural language inference. So basically, you're given a prompt, right? So that's the portion in yellow. So these are, let's say, 2 observations. Jim was working on a project. Luckily, he found it on a nearby shelf. And what you have to do is select a hypothesis that is most likely to be true. So that's why it's abductive rather than deductive. And in this case, Jim found he was missing an item is most likely the hypothesis that is connecting the 2 observations. So we need to get machines to do this, and then they are evaluated on accuracy, right? So this is what we call multiple choice question answering. And such data sets can be manually created, automatically generated, crowdsourced. They've been done in all kinds of ways. They test different aspects of common sense, such as social intelligence, physical intelligence, ANLI, and so on, right? So far, it's so good. But unfortunately, this kind of evaluation has limitations. So first of all, right, if we think about our common sense, we don't go around, answering multiple choice questions. There is so much more than that to human common sense. And even if we ask such questions, current benchmarks treat each question as an IID instance. So, there's no, it's sort of like it's like taking a standardized test. You answer a question, you move on to the next question, to the next question. So it's kind of these small mini tasks rather than sort of more comprehensive task with dependencies and planning and so on. And there's a real sense in the community that many of the benchmarks have been gamed due to continuous testing. So even before ChatGPT and all these big language models, some of the earlier generation of language models like Unicorn were already coming very close to human performance on physical IQA. And I think we can sort of agree that we are very far away from true physical intelligence and even state-of-the-art AI. So from some of the leaderboards, that's what you would believe, but it's not true. So something is wrong with this kind of evaluation. It has merits, but it should not be the only thing to evaluate machine common sense. So what we are suggesting and proposing is this context-rich method for evaluating machine common sense. And as you can see here, this is sort of a more sort of iterative, open loop session. That's what we call it. So in this one, it's almost like you're conducting an interrogation with the machine, but with the goal of evaluating common sense. So let's say that you start by testing the comprehension abilities of a machine. So you give it a context, you ask a question, you ask it to give you an answer, but then, right, you can ask a follow-up question, testing counterfactual reasoning, and you can ask a follow-up question. And so we have actually done this kind of evaluation with ChatGPT and with some of the other language models. And it turns out that this is a richer way of evaluating machine common sense. And this method, in fact, shows that although the big language models are getting closer, they still make mistakes that you would not expect from an entity that has common sense. So if you're interested, come talk to me more, and I'll be happy to show you our ChatGPT logs and walk through some of the findings that we have encountered. So, yeah.
Thank you very much. And that was really interesting. Hao Zhang, tell me how I'm pronouncing that. Hao Zhang is here to talk us through coherence in intelligent systems. Thank you.
Is that okay? Well, thank you so much for bringing me here, and it feels fantastic to this big family, I think. And the topic that I wanted to share with you today is the neural coherence for general intelligence. And can anyone have a guess about what I'm going to talk about? I think most topic here is very hard to predict what the people are going to talk about. So I will show you in the next following minutes. So the basic motivation is that, in my personal opinion, as far as I know, that all living systems, as large as human beings and as small as a single cell or virus, could surprise us now and then with their mysterious behavior that I think is intelligent. So, and the generality of their intelligent behavior is still far beyond most current artificial systems. So I wonder what is the gap between the two types of systems. And perhaps one of the basic fundamental difference between the artificial and living system is that the artificial system usually use the equilibrium state to represent things like the object, features, concepts, symbols, or relations, like the static feature map in a feed-forward neural network. The living system, on the other hand, prefer to use non-equilibrium states to, to operate or to like operate in non-equilibrium states that is indicated by various type of rhythmic behaviors and transient synchronies. And now here, the neural coherence generally refer to those spatial temporal states that a large amount of computing units that is correlated together so that the synchrony and rhythm emerges. So it seems to me that coherent state is indeed a very important state for some essential mental operations like consciousness or awareness. And in the temporal spatial theory of consciousness, Nors proposed that the nestedness of temporal and spatial structure of the neural activity could account for the level of the consciousness. So it seems that coherence is indeed an important concept. So my question is, how can we conceptually link neural coherence to the general intelligence? And on the other hand, can we build up neural coherence to solve computational problems that is related to AGI? So that is the basic thing that I wanted to discuss. And the key picture and the main point are summarized in this page. From a point of view of searching in a dynamical and distributed system. So there are two general assumptions, very general, maybe too general. And the first one is the AGI needs to search for solutions of various levels, one after another, for its goal, for its survival. So it needs to search. The second one is that the system itself should have a way to know when the solution has been found. In other words, the solution should be indicated. Based on the two assumptions, I will show that what is the dynamical nature of the neural coherence and why it is important for AGI and how to build up neural coherence based on principles. To be more specific, at representational level, I think neural coherence is a temporal aspect of the solution itself that is represented as cycles. And at functional level, I will show that neural coherence could serve as indicators of the solution. And what is special is that coherence could act as universal and internal indicator in a distributed system. And at implementational level, I show that the neural coherence can build up from principles, and the principle is called self-evidencing. And at implementation level, I show two demos on two general computational problems that is related to the emergence of perceptual awareness. The first one is the bidding problem, a very old problem in psychology, neuroscience, and neurosymbolic literature. And this problem cares about how distributed informations like different features like color, shape, texture, voice, you name it, those distributed information could combine and be grouped or bound together to form a whole entity or whole object. For example, a percept of a person that we recognize. And the temporal bidding theory guesses that the bidding information could be expressed as neural coherence, like here. And the second problem is the part-whole hierarchy problem, a very challenging problem for distributed system, which asks how to dynamically form a parsing tree of a scene or of a concept in a neural network. So a tree in a neural network. And my guess is that the nested structure of the part-whole hierarchy could be accounted for as a nested temporal spatial structure of neural coherence as here. And that is my demos. And to sum up, In both cases, the solution is searched in distributed system and is represented as coherent state. And that is the sketch of the model. And the basic principle behind is very simple. In a word, it is neural coherence could be built up from self-evidencing between two things. One of them is the top-down attention, maybe by a word model. And the other is the bottom-up called incidence filtering or coherence filtering. And here is a snapshot of the results on the grouping problem or the binding problem. Well, given the ambiguous input, the system needs to search for solutions so that different objects could be segregated. And starting from random state or random guess, the searching gradually converges to the coherent state, indicated by the coherence measure. And in this state, the binding solution is represented as the neural coherence. And along the way, the gamma-like oscillation emerges. So this process is inspired or similar to what is happening in the neural cortex. And for more details about the model, the result, or the idea behind, welcome to my poster and discuss. So thank you very much, that's all.
Thank you so much, sir. How? All right, folks, this was absolutely thrilling. Thank you for these very highly talented, skilled researchers for all these papers. We're going to just do a very short Q&A because we've got posters outside, we've got some demos. So I'm going to take one question from YouTube, one from the audience. And there's one that's been waiting on YouTube since this morning from Yasantha, is asking Mohammed Reza Ali Doost, who's still with us today, this afternoon. And Yasantha asks, thank you, Yasantha, for your questions, asks, is the VEI values of narrow AI versus AGI? And can VEI consider as a valuation aspect of AGI? Mohammed Reza, I hope you understand that. And
hello
already.
again. Yeah.
Hello again.
Hello again. Thank you for your question. I have to mention that, let me share my screen shortly. I had to omit this portion, this section, because of the time limitation. Versatility and efficiency, which I designed VEI based on this, are two necessary conditions for AGI. An AGI agent has to be versatile and efficient. And what does it mean? Based on the two definitions from Leckhatter and Penetschin-Gerzel, versatility means a wide range of easy to complex environments, and efficiency means perform well. And when we talk about AI, we are talking just about efficiency and not versatility. And when we talk about AGI or NGI, like what is happening in humans, they can also perform well in a wide range of easy to complex environments. So they would have a higher amount of VI, and they can perform in a wide range of environments. But AI just perform well, but in a specific and narrow range of environments. So the VI for AI is low, and the VI for AGI and NGI are high. Thank you very much.
Thank you very much, Mohammed Reza. Thank you for your paper. Right, any questions here in the room? And also, I think all of our speakers are going to be out with posters anyway, so you get a chance to go speak with them individually. Anyone in the room? I'm going to closed. All right. Well, folks, that's the end of the presented sessions for AGI 23 June 17th sessions. Thank you all very much for coming. Thank you all very much to our speakers for your papers.
I want to share that all of the papers and posters are available online on the AGI-23 website. So you can look at the abstracts, look at the authors, you can download the papers and the proceedings. The full proceedings are available on the website as well. So you can dive deeper into any of these topics that we only got to touch on today.
Thank you very much. I'd also like to share that anyone who's got a demo to show, please go upstairs, one floor up. There are a number of big screens, 3 or 4 big screens, which you can plug into and use that for your demo. And people can just huddle around you. The posters are all here. We'll be back tomorrow morning, 8 to 9, pre-lobby, presentation, drinks and refreshments and gathering. And then we're going to kick off at 9 a.m. sharp. So have a beautiful evening tonight. Thank you so much to all of our YouTube audience for your engagement, your questions, your comments, and for following along. And we'll see you all tomorrow as well. Good night. Yeah,